4. Go ahead, guys.
Thanks, Laura. As Laura said, we're talking about Paradise 3.4, which we are all very excited about. This is existing software that came out about a month ago, so it's not something that's going to be coming out. It's out there now, and everything we're going to be showing is currently available. As a lot of you know, this is not an intro to Paradise, so for that, I would say if you're interested in that, go to some of the other talks. This is more for existing users that are familiar with Paradise. So we're not going to spend a lot of time talking about the basics of Paradise. But Paradise has given interpreters the ability to detect significantly more detail in their seismic data. And anybody that used Paradise realizes that. And as a natural extension of the current software was the ability to compare these results to the ground truth, which are well logs. And so you have your SOM and your geobody outputs. You'd really like to compare those to logs. People have been doing that, but it's been cumbersome. They've had to go to other applications, and some of them have just been doing it in PowerPoint. So today, Paradise is now capable of displaying digital well logs, TD charts, formation tops, and cross sections. And we hope that it's in a simple and straightforward manner so you can construct these things easily. So in this presentation, we'll be discussing the new well log cross-section functionality, the GPU support for AASPI, and AASPI is the consortium out of the University of Oklahoma run by Kurt Marfit, and the latest Petrel Connector. In addition, and probably most importantly to this presentation, is a demo by Sarah Stanley, who will show some of these new tools using the offshore New Zealand Maui data from the Maui field. And she'll be walking through all of this functionality. Okay, so our agenda is we'll do a little bit of work with the well analysis, show you some of that new functionality. Then I'd like to mention the GPU support for the AASPI algorithms. Then the Petrel Connector 2020. And then we'll turn it over to Sarah, who will give a brief background on the Maui field and then show the demonstration. I'm going to open up my laser pointer here. So I have that available. Okay, before we jump in, I wanted to give everybody a clear picture of what we're doing at Geophysical Insights and where we're heading. You know, we're building an interpretation AI machine learning toolkit for the interpreter that today includes the following functions that you see on this slide, but over time will be augmented by the company and hopefully by users. So we continue to add tools. Some of these you're familiar with, like SOM, which is represented here. Attribute selection is our PCA. As you all know, we have our 2D color map. But you may not be familiar with our deep seismic facies classification or deep learning, or the fact that we are playing around with GPUs for the AASPI applications, and we have several of those that are in this latest release. And the other things that we were talking about today are the well log visualization tools. So anyway, I wanted to mention that because, you know, we're not trying to build a single application. We're building a toolkit, and we want to deliver this toolkit to the interpreters so that the interpreters have enough tools to do what they need to do and make it easy for them to use and interface with the application. So why the well log cross-section module? Why did we develop that? As I mentioned, you know, our ability to detect information at a much finer level in seismic data just leads to you wanting to tie that to the well logs. So this necessitated us having well log displays, TD charts, formation tops, cross sections, and be able to manipulate those with our own data. So all of the results that we come out with, and be able to look at these together in an easy to use manner. So we needed to extract data along the borehole. And this can be any data. So any data that we can put in our 3D viewer, SOM results, lithofaces, even probability results. If you were looking for some measure of a fault that you could see in a log and you wanted to see if there was a representation of that in your seismic data, that's another application of this. And then we wanted to be able to have enough metadata associated with these tools that you could easily tie things to your individual displays and not have to update them all the time. And we'll talk about that in more detail, and Sarah will even show that. So now in Paradise 3.4, we have an easy way of doing this. And that's really the focus of what we'll be showing in the demo. So the well analysis, there's 4 components to it. Number 1 is the ability to extract any seismic volume along a wellbore. You have to have that. And like I said, this can be any volume, seismic attributes, result sets. Then we needed the ability to build a cross-section with multiple wells. And we wanted to be able to do that from 2 different places in the application. One from the well manager, if that was, or to be able to do it from the 3D viewer. Then we needed some increased functionality. It's not unusual that when you're interpreting, you don't know what TD curve to use, so you're constantly playing with those. We needed some tools to see the results of that. And then we wanted to have be able to rename some of the logs, and you'll see why that's important in a few minutes. And then we also needed data import and export improvements. So we never used wells before within Paradise, had those as a data type. We had to incorporate that in the application. And as part of that, we can now read in partial OWX information, and we can export logs via LAS. Here's an example of the volume extracted along a wellbore. This window is from our 3D viewer, and you've got several pieces of data in this window. This is the SOM output with the associated 8x8 color bar. And this is a classification of 64 different groups based on a multi-attribute input. And through that, we have the Maui #1 well, which passes through the data. These are formation tops labeled on the well. And then over here, we see a piece of our new well display. And here we have the Maui gamma ray log that's colored to highlight sand and shales. And next to that is the SOM output along this wellbore in its own color bar, which is the color bar that's over here in the center of the 3D viewer display. So that's the same color bar. So now we have this really nice direct comparison of a well log to, or in this case, a gamma ray, to the SOM output. Both of them with their own associated color bars. Now, these are examples of other types of information that can be extracted the same way. In the case on my left, you can see the seismic attributes. Any attribute can be in here. In this case, it's amplitude, and it's colored with its own color bar. In the middle, we have the SOM, which is colored with this color bar that's right next to it. Then we have a facies classification. And then the last one on the right is the fault probability or a fault detection volume extraction along there, and with its own color bar. So really what I'm saying here is that anything we can put in the 3D viewer, any volume we can extract and manipulate along a wellbore now, and compare that to any item that we want to compare it to, any well log or any other volume. And in this case, this is not this could be, it's the same well, but you know, it's a cross section essentially of different types of data. So how do you build a cross section with this? And in this case, we're going to be looking at, and this will be something that Sarah will emphasize in her demonstration, we're looking at 3 wells. We have the Maui #1, we have the PBP8 well, and then we have the Maui #7. So we made a cross section here with the gamma ray for each one with its own color bar, highlighting again sands and shales. And then we have the SOM for each of these wells with its own color bar, the same for each of these 3 SOMs. There's no difference between those. And they're compared, these are tied, these are shown in measured depth, but you can flatten them to a formation top if you want to. And the formation tops, they're a little small in this display, but here they're labeled here. Here's another one down here. So they're displayed. Then you can save this as the CGM. You can plot it, or you can save it as a picture. The thing that's interesting about this was able to be put together in 45 seconds. And you'll see that in the demo. It's very easy to manipulate these things and change things like color bar and other things, scales, other things that you may want to change quickly. And that was the whole reason for putting this in Paradise. We know there's a lot of applications out there that do cross sections, and we're not trying to duplicate all that functionality. We wanted to highlight some key functionality for our application and our type of data that's easy to use, that any interpreter can learn to manipulate very quickly. Here's an example of some of that other increased functionality. We talked about TD charts. So we needed a tool where we could actually change the TD chart and make it active and see what results that would have on our conversion from time to depth. And if you look at this, you can go up to the right here and select which chart you want to use for your TD chart. And then you can get a quick view of how that affects the data and where it's being put. So, you know, as you go through these TD charts, as you know, if you've worked in a field, there's a lot of TD chart information. Some of it's good, some of it's not. Some of it fits the data, some of it doesn't. So you have to look at these and you have to decide which one you're going to end up with. Once you do decide, then you make that one active and it can stay throughout this process. Here's another example of the interface, and I'm just giving you a few highlights on the interface here. But what's interesting about this gives us the ability to add a lot of metadata for each of the curve types that we're associated with. And some of this metadata includes just text information. Other things are like the color bar. So this metadata, as you go through the process, is carried through. And there's some things over here like curve type. You can actually change the curve type. So in this first one, deep resistivity, once I've named something deep resistivity, and say I have 10 wells that I'm looking at, and I label a curve type deep resistivity, then I can go in and just sort on those. And I can associate other metadata like color bars to all the deep resistivities, all at the same. So I'm not constantly changing things and having to bring in, every time I bring in a new curve, I have to assign a new color bar, I have to do a new scale, I have to do other things that you would normally have to do in some other applications. So we've tried to make it very easy to use by adding a lot of this metadata. And this metadata can be applied not just to a well curve, but it can also be applied to a classification, a probability volume, any volume that, again, you can put into the 3D viewer. Okay, let me talk about AASPI a little bit now. I'm going to switch gears. And some of you are familiar with the AASPI Consortium. The AASPI Consortium, and AASPI stands for Attribute Assisted Seismic Processing and Interpretation. It's a consortium that's been around for quite a while, and it's at the University of Oklahoma under Dr. Kurt Marfit. And it's been a very successful consortium. And really what they do, it's a centerpiece for research into geometric attributes. Now, a lot of these geometric attributes are slow. And we, as Geophysical Insights, we have the right to market the AASPI library from the University of Oklahoma within Paradise. And in our version of AASPI, the most common default parameters have been tested and selected, and the required connections between different attributes is pre-wired. So, for example, in 3 of the attributes that I have up here on the screen, the DIP3D is required to run the GLCM. So normally you'd have to run the DIP3D, then you run the GLCM. Well, in our application, it already knows that. So when you go to run the GLCM, it'll give you everything you need for the DIP3D, and they'll run concurrently. Or if you don't have the DIP3D in there, it'll tell you that it won't run. So all of that is hardwired to make it easier for the user to look at. So we looked at three of these attributes that do take a long time to run, even with a multi-core machine. And the numbers I'm going to be comparing here on the next slide, you'll see the kind of speed up that we got. So DIP3D, that's measuring using the gradient structure tensor and some complex semblance scans to get an idea of the dip of the volume. So that's one of the attributes. The lower upper middle dip filter, this is a smoothing and sharpening parameters to limit the smoothing characteristics of a normal median filter. And it tries to find a balance between the structural, enhancing the structure, and while preserving the faults. And then the GLCM, which stands for gray level co-occurrence matrix, this provides a measure of texture. So starting last year, we started looking into running these things on GPUs to kind of speed them up, because if you have a decent sized survey, these things can take days and days to run, even with a machine, like I said, with a multi-processor machine with a lot of processors. So the numbers I'll be showing here, here's the attribute in the left column. In the middle is the speed up that we got. And the video card that we were using to do this, since there's only one video card, you can run these with multiple video cards too, is for the LUM filter, it was 50 times. For the DIP3D, it was 3 to 5 times. For the GLCM, it was 3 to 7 times with this Quadro RTX 6000 NVIDIA card. And that's a medium priced NVIDIA card. And again, we're only running one. And this is compared to, these speed ups are compared to 36, a 36 processor machine. So it's, we're comparing multiple CPUs compared to the one video card. So if you're comparing one CPU to these, it would be another factor of 30 in there. So it's a big speed up in what we're seeing. And I don't think, we are still tuning these, so I'm not sure that they're totally finished, but we'll probably get some more performance out of the last two before we're done. And we've also been working on curvature. For those folks out there that like to run curvature, that's another one that we're finishing up right now. It's in the testing phase and will be available shortly within the application. Just to give you an example of the interface that we have in Paradise for the AASPI attributes, here's an example here, and this is what I was talking about, where here we're running the GLCM, and it knows that we need to dip. All these parameters are filled out based on your data, and so you don't have to go in and do a lot of parameter searching. And then for the AASPI parameters, we've taken what we consider the best defaults, and those are in there. Now you can always override those if you know something about AASPI, but AASPI is basically an expert system, and it takes a long time to understand it, know all the parameters. So we've tried to make that easier for our users. So everything that AASPI has available up until its latest release is available within Paradise, and we'll be doing another update of this probably towards the end of the year or into first quarter. Finally, I wanted to talk a little bit about the Petrel Connector 2020. As a lot of you are using Petrel 2020, we had to update our connector to work with that. And we also had to do some other things. So in addition to working with the latest version of Petrel, we had to, now that we have log curves, TD charts, extracted curves within Paradise, we needed to connect those up with our Petrel connector also. Likewise, the color bars that are associated with these extraction curves will come over with the connector. And it should be noted that if you are on an earlier version of Petrel, this functionality will work with Petrel 2018, 2019, and of course 2020. We are not supporting 2017. So if you're on 2017, it's probably time to upgrade your Petrel application. Okay, now with that, I'll turn this over to Sarah Stanley, who has a couple slides, and then she'll jump into her demo. Sarah?
Thank you, Mike. If you can advance to the first slide, please. This is just an overview of the Maui field offshore New Zealand. It's part of the Taranaki Basin. And you can see this has been divided up into the Maui A in the north, the Maui B in the south. The reservoir, it's Eocene. It's identified with the Mangahiwa sea sand from the Kapuni group. And you can see there is the Watiki Fault on the west, which is a nearly vertical fault, and the Cape Edgemont Fault system to the east. Now, the Maui A area is pretty much entirely gas. The Maui B area is predominantly gas with some gas condensate. And there are two anticlinal features that are separated by a saddle, which is why we call them the Maui A and the Maui B area. Would you mind going to the next one, please? Now, in identifying our target for study, the Tikarangi limestone is an excellent marker. So we mapped the limestone so that we could go down from that to the sea shale. Our environment is going to be the sea zone. So starting with the sea shale, and then we have the top of the upper C1 sand, the base of the C1 upper sand, and the top of the D sand, and that's our zone of investigation. Can you give me the next one, Mike? This is just a stratigraphic view showing the gamma ray curve of our C zone with lithology from the core. This is from the Maui 5 well. Then we have the photoelectric effect curve, and we have a supervised ANN extraction for lithology using the gamma ray, the NFI, the rho B curve, the photoelectric effect curve, and the deep resistivity. And you can see that the C is divided into the upper C1, the middle C2, and the lower C3. And combined, that's about 300 meters. Now, using the velocity of the interval velocity of the field, our tuning thickness is around 90 meters. But we're able, with our enhanced interpretation abilities in Paradise, we're able to look at sands that are a thickness of 10 meters or less, and that in English translates to about 39 feet. So Mike, with that, I think I'll start my demo. So I'm going to share out my screen. And hopefully,
That's it.
Okay, hopefully everybody can see my screen. And this is your typical Paradise homepage. I just clicked on the home and I'm at the home page. Now, as Mike said, there are several different ways that you can get to the well cross-section viewer. One of them is through data management, well manager, and you just right click on a well and you can go to the well cross-section. view. However, I'm going to take you through another way, which is the way most interpreters would probably want to get to the viewer. I'm going to go to the 3D viewer. And I'm on a different machine, so there may be a slight lag time. I'm going to filter on the Maui field, and I'm going to go straight to my wells. Now I have all of the wells. I also have a subset of tide wells, and these have been tied through Petrel with time depth charts. So I'm going to just pick all 3 of those. Now I can take these over to the visible well pane, bring them up in Paradise in the 3D viewer, and then I can go at the top to wells, well cross section. They immediately become vertical, and I can select each well for my cross section, right click, and then send to the cross section view. But there's even a faster way to do this, and that's simply to go back to the wells, go to my subset of tide wells, and just manually drag and drop those 3 wells with the right mouse button, and then go to right mouse button, click, and go to the well cross section view directly from the subset view. Now, I'm going to close this out so that we can get back to our well subset. And I'm going to come right down here and bring up my well subset in the well cross section view. And as you can see, I have already chosen what formation tops I want to make visible. So just use my formation top visibility, and I can turn these on and off as I choose. And notice that the wells are not equal in depth. That's because there are some small faults in this field. So I'm going to choose to flatten on my sea sand, which is my main reservoir. So there I flattened on the sea sand, and so all of them are at the sea sand level. Now that I'm on the sea sand, I'm going to highlight that because that's my area of interest. So I'm simply going to change the color of my sea sand formation top, and that will change the sea sand on all of the wells in my cross-section view. So now that I have the wells, you can see here's the first well, then the second well, and if I scroll down, then the third well. So what I'm going to do now is I'm just going to come into my depth track, and I'm going to add a track, make it linear to the left, and I'm going to do that for each well. And we do this manually because we have the ability to set individual tracks for individual wells within the view. Now I'm going to focus on this well, which is the Maui-7. So I'm going to come in here to my depth track, and I'm going to add 1 additional track to the right. I'm going to put my logs in these tracks based on the track properties. So now what I want to do is I want to take this second track, and I want to change the track properties and make this track, instead of linear, I want to make it logarithmic. And I want to change my vertical decade from 4 cycles to 3. Now I'm going to start populating my tracks. So the first place I'm going to populate is with the gamma ray curve. So I'm going to just drag and drop the gamma ray curve into each well in track 1. And notice that, and as interpreters, you notice that they don't always recalibrate the log curves before you get a hold of them as an interpreter. So you may have to go in and recalibrate your curves. So I'm going to just click on the gamma ray. You can do this a couple of ways. You could click on the actual curve itself, but I'm just going to come up into the header and click on the gamma ray. and then hold my control key down, click on the next well and the third well, and then do a double click, and notice that I have auto scaling. Now, for some reason that didn't like that, so I'm going to do it again. Now I have my multiple curves selected. So I'm going to change my gamma ray limits to 0 on the left and to 150 on the right, because I've studied the wells in this field and that's a good range for the gamma ray curve. I'm going to make it linear, and I'm going to leave the color as kind of a forest green, and the line width is 2. Now we have given you some default colors and styles, line styles for the log curves, but you can always go in and modify these depending on your company's preferences. So I'm going to say OK, and now I have my gamma ray curve. In this particular well, I'm going to add a resistivity curve, so I'm going to come back up to the top, scroll back up, and I'm going to add my deep resistivity. And again, I'm going to come up to my header, and I'm going to set the scale for my resistivity from 1 to 2000. And remember, it is logarithmic. And I'll just apply that as the default in case we bring in any other curves. Now you can begin to see where the reservoir is starting to indicate low gamma ray API units for clean sand, high resistivity. Let's also add the density curve. And my density is going to be from about 1.98 to 2.98. And again, I'll apply that. And then I'm also going to apply my neutron. Because this is a gas field, there should be crossover in the reservoir. And I'm going to change my neutron scale from 0.45 or 45% to a negative 15%. And again, you can say OK here. So now I've got my neutron density crossover. So this really is indicative of the reservoir. Clean sand, high resistivity, neutron density crossover. Now, once we have our log curves, it's nice to be able to read what the curve is reading. So I'm just going to come up to the tools and go to my tooltip options, and I'm going to turn on for curve name, depth value, and the units. Actually, I'm going to turn off the unit and give us the log value. And I'm going to make it active on my mouse. I also want to add a background so that it's a little easier to read, and I'll just make that a bright yellow. Now, as soon as I activate my tooltip, when I come into my log curve, notice immediately if I put my cursor on my gamma ray, it's telling me the depth in meters, and it's also telling me the gamma ray or the API at 37. This will be active for the resistivity and the neutron density crossover as well. Once I'm finished with my tooltip, I simply just come up and turn my options off. And now I'm back to my normal display. The other thing we're going to want to do is shade our density curve so that we can see, and also I'm going to shade my resistivity in a minute. But I want to come in here and highlight my curve. And then I'm going to go to my curve properties. I simply double clicked. You could also do it from the icons at the top. I'm going to go and I want to do a right fill. I'm going to use my right border as my boundary reference line. My fill pattern is going to be a one-dimensional color map. And I'm going to come down here, and I have a couple of color bars that I brought in from another application. It's very easy to import color bars into Paradise. And I'm going to come in here, and I am going to pick my gamma or my gamma ray. Now I'm going to use the gamma ray curve. And notice that it's staying off. I'm not seeing it even though I picked it. That's so that you as the interpreter can determine when you want to make it visible and when you want to hide it. So I'm going to turn on Make Visible. And now my gamma ray shading will be visible along my gamma ray track or curve in my track. The other thing I want to do is I want to highlight my resistivity. Say I've got, I'm going to use left fill. Say I want to highlight everything that's greater than 30 ohms. So I'm simply going to make visible, and instead of using a reference line or a border, I'm going to use a baseline at 30 ohms. I'm going to use a solid fill pattern, and I'll just make it red. So everything that is high resistivity is going to be highlighted with a red shading. So this tells me I've got good clean sand, high resistivity, and my neutron density crossover. What makes our cross-section tool so powerful, as Mike alluded to earlier, is our ability to bring in, if you can see it in the 3D viewer, if it's any kind of seismic data, we can bring that into the log view. So what I'm going to do here is simply go into my seismic well log extraction, click on the wells for extraction. I'm going to filter on the Maui well again, and I'm going to go back to my tide wells and bring all of those wells over. Then I'm going to extract data. And my data extraction, I'm going to just do one SOM result. So I'm going to go to my result sets, go to this particular SOM, SOM 1.1, and that's going to be added to the result set. Now notice it's result set or sets. I can extract multiple data types simultaneously with this tool, but we're just going to do the one today. So I'm going to say okay to that. And then we can do a description if you want, a prefix. If you're working in a team, you might want to use your initials for a prefix or a suffix. I'm simply going to use the extract button, select that. Now, this is a long name. It's good when you're working with your SOMs to have very descriptive names, but I don't want to, and I'd already extracted it. I don't want to worry about such a long name. So what I'm going to do here, I'm going to do it again. Data to extract. I'm going to extract the same data type. This time, before I extract, what I'm going to do is I'm going to stretch this out, and I'm going to say okay to this, and then I'm simply going to cut off the data name so that we're just doing the descend top. And I'm going to come in here, and I'm simply going to delete everything to the right of descend top and extract that. Now this will mean that I will have a much shorter well log curve. And notice how fast it is. It's already completed. So instead of having a log curve this long, I'm having a log curve named this long. And notice that not only does it extract the classification, it also extracts the probability. And remember, these are now log curves, so they can be exported as a log curve. So I'm going to come in here and I'm going to drag and drop my extracted SOM result onto all three of these wells. And this is why I left these two wells blank, so you could see with the log curves and with just the SOM itself. Now, this is all well and good, but I want to see more detail. So I'm simply going to come into my log, my wells, and I am going to zoom in on them. And then I'm going to zoom in one more time. And this really allows the interpreter to see the whole package of the seismic data with my clean sand gamma ray, my high resistivity, and my neutron density crossover, and you can see what SOM results, what neurons are associated with pay versus not pay, which is something that you would see up in here. Very powerful tool, very, very easy to use. So once we've extracted our data, we need to be able to manipulate the data. So we have added to our data management tools. We have in the Wells Manager, and Mike showed you this earlier, but I'm going to show you again. We have the Maui data, and I'm just going to come down here to one of the Maui wells, the Maui 1, right click, and I'm going to view details. Now, we greatly expanded this well data management tool. As Mike showed you earlier, you can see all of the curves. In this case, I've got depth, so I'm simply going to name a curve type and come down to depth and assign depth to that curve type. Now, I don't have any active time depth chart because these are curves, but when I go into my area where I've extracted the seismic data, it shows me my active time depth chart. Coming down into this area of my display, I can see my time depth curve, the active one. If I want to change the active time depth curve, I simply come in here and this becomes visible. So if I wanted to change to a Maui 1 time depth curve from a Wiener-Levinson synthetic, I could simply make this the active time depth chart and it would become the active time depth chart. When I go back to the existing time depth chart, that disappears. So that button will only become active if you're changing the time depth relationship. So we can assign curves, we can assign curve type, we can set active time depth charts for our attributes, and we can see the extents, minimum and maximum values, and the number of neurons or labels for our extracted well logs. In addition to the well management, we have also expanded our well log type manager. And because we have brought in the expanded log functionality, we've given you the ability to add additional log curve types and change their display as well. So I'm going to come down here and I'm simply going to add a new log curve type. And it's early in the morning, so I'm just going to call it ZZZ. make that active, and then do a right mouse button click. And I can open the curve type details. I can change the line color. I'll make it orange. I can change the line style to dashed, and I can determine the line width. I can also give it a description. And simply save it as a new curve type. So in summary, the well log cross-section viewer is giving us the ability to actually bring our SOM results from our seismic data to the actual borehole and display it with well log curves, beside well log curves, and also to shade our log curves for better clarity and understanding. So with that, I'd like to say thank you. And if you have any questions, I'd be more than happy to answer them for you.
Thank you very much for that, Sarah and Mike. We certainly appreciate it. You can now type your questions in the chat box, and then Sarah can answer those verbally. If you're watching this on our YouTube live stream, you can click through to the comments and then post your question there, and we can get that. It is something to note, the YouTube live stream is about 30 seconds behind this video, so we'll wait a couple minutes to make sure that everybody gets the message. Okay, you're welcome to type your questions in the chat. Are you looking for those? All right, very good. Well, if there aren't any questions, then we encourage you guys to stick around for our next presentation at 10 o'clock, where Tom Smith will be presenting on machine learning for incomplete geoscientists. Thank you very much, and we'll see you shortly.
Yeah.
Yeah, loud
Yes.
and clear.
Well, that's good news.
Tom, you ready to go ahead and get started?
Yeah, I'm turning my camera off.
Okay.
Let's roll.
All right. Well, we're going to go ahead and start the recording. Hello, everyone, and welcome. Dr. Tom Smith is going to present Machine Learning for Incomplete Geoscientists. Whether you're joining us today on Teams or you're joining us on the YouTube live stream, feel free to ask questions in the chat. And at periods within this, Tom will take a break and be able to answer those questions. So without further ado.
Hello, everyone. Welcome to this presentation. The title, Machine Learning for Incomplete Geoscientists. You need to read that a little carefully. It's not machine learning for incompetent geoscientists, it's incomplete. And it's also for geoscientists, both geologists and geophysicists. Yes, there are still a few remaining geophysicists like myself, and I guess I'm a little bit of a geologist. If you're a geophysicist, if you're doing interpretation, you've got to be a pretty good geologist yourself. So anyway, we're going to focus on the new stuff in the upstream oil and gas geoscience analysis, and that is the use of machine learning. So as we have indicated here, it's machine learning with a red M, red L. So if you want to get on the inside real fast, if you consider yourself incomplete, an incomplete geoscientist, and you want to pick up machine learning, well, become an insider right off the bat on the first slide here. We're going to talk about ML. We have had an abstract for this presentation. I'm not going to bother going through that here, but we are going to cover a lot of ground this morning, covered on a kind of a light scale, and we're going to cover a number of topics. So you could say, well, yeah, this is a presentation to 50,000 feet. There's no meat here. Well, hold on, give me a break. Yes, there's going to be some meat here, and we'll show you several examples. I'll show you a geophysical example of the use of machine learning, and then we'll end the presentation with what I think is a very important geoscience application. It's got a lot of reservoir characterization geology in it as well. So I'd like to begin this presentation, not to be provocative, but I'd like to start on a kind of a high level here, and let's ask the very simple-minded question, which you probably have never thought about, but is there really any science in geoscience? Well, hello, geologic science and geophysics science, they're a little bit different. In fact, in some regards, they're sort of at loggerheads with each other. They sort of, they're different, and they sort of sometimes collide, they sometimes pull apart. Well, the geologic sciences are based upon broad principles applied across vast areas of Earth volumes. And unfortunately, geology is only known through some very slender boreholes that run through the Earth. But the science often lacks specific predictions due to what? Due to abrupt changes in the geologic conditions, so the depositional patterns have changed, and also slow geologic changes in the Earth as you cook the mud into stone. Now, there are severe climate changes in the Earth's history over time, and there's been tremendous tectonic forces, and they have been throughout all geologic history, and they certainly affect our sedimentation and erosional rates, and it also affects faulting and other natural catastrophes. Okay, so that's our geoscience. That's our geologic science. Geophysical science is a little bit different. This is where the loggerhead begins. Now, it's based on well-founded physical principles applied broadly, very broadly, to the mechanical properties of heterogeneous rock. Very seldom are we lucky enough to have something that's homogeneous. Now, in the geophysical science, they have been indirectly inferred through both surface and borehole measurements, and we have a resulting image of the subsurface. So better than an MRI of your lungs, we have a seismic image of the Earth that's often three-dimensional. However, the science, as the geophysical science, it advances slowly. Why is that? Well, because of the meticulous acceptance of the images only through drilling validation. If they're not validated by the drill, it's not science. It's not doing what we want it to do. Well, I'd like to sort of draw you now into consideration of these four people up here. Let me introduce them to you, please. Claude Shannon from Petrel, Michigan. Alan Turing from Maida Vale, which is a suburb of London, England. Tom Mitchell from Blossburg, Pennsylvania, and Arthur Samuel from Emporia, Kansas. These four people are really worth our high regard for the following reason. We're going to take a look at three pillars of the development of computer computations. These absolutely are fundamental. And it is these four individuals whose minds soared beyond those of others, far beyond others. Let's take a look at these three pillars. Pillar number one was by Claude Shannon. Claude Shannon is a very interesting, he was an MIT professor, wandered out of the Midwest, ended up at MIT, and he was the author of something very profound. And that is that information may be transmitted without error through binary communication channels. That's profound. All the time in the past, you have AM radio, FM radio, any way you want to transmit information across the communication channel, it always had error of some kind. If you were really good, it reduced to Gaussian error. Claude Shannon realized that you could transmit information without any error at all using binary communication channels. Second concept that is a pillar. Computer memory can not only store data, volatile data brought in and stored in memory, but it can also store the computer instructions that operate on the data. And that's absolutely fundamental, Alan Turing. And the third that is a pillar of the development of computer computations is that computer algorithms can adapt themselves to the data. That's absolutely fundamental. And as you probably got this one figured out, yeah, this is machine learning, isn't it? Information can transmit without error, and you can store in the computer memory not only the data, but the instructions, and the computer algorithms can adapt to data. Tom Mitchell, Arthur Samuel. I've included a picture of Alan Turing here. If you ever have seen the movie on Alan Turing or read his bio or things like that, very brilliant, but literally a tortured soul. So what we're looking at here is Alan Turing as a PowerPoint or Photoshop cutout on top of a printed circuit. And it's when he was working during World War II, there were no such things as printed circuits, but he really is the father of brilliant mind that put a number of these things together. The whole concept of CPUs and computer memory and how you move things around and how you operate on data. Whole concept of I/O devices. All right, now those are the three pillars, and now let's take a look at the whole concept of machine learning. Now, I'm sorry, we're going to start at 50,000 feet here, and I know you've got your oxygen mask on, and that's good. We're going to start here with three concepts: self-adaptation, self-organization, and self-awareness. Well, self-adaptation, what is that? Well, self-adaptation means that the machine algorithm adapts itself to selected characteristics of the data. And it stores these results in a storage structure. Typically, it's a neural network. That's self-adaptation. That's probably what you think of when you think about machine learning. That is self-adaptation. But there's a couple other things here, and that is self-organization. Well, self-organization is the next higher level. because it's not only self-adaptation, but the organization of the neural network itself is organized into patterns. It's self-organization. And you might think, oh my gosh, that's pretty sophisticated stuff. Well, hello, not really. Even our brains are self-organized. The visual cortex on the back of your brain, that's one area. Well, we have different areas of our brain for different functions, things like that. Well, even within the visual cortex, when you're looking at different patterns, it's changing in self-organization in the visual cortex itself. And there's one level even further than that, past self-adaptation, past self-organization, and that's self-awareness. That's self-organized neural networks from before, but it adapts not only to the data, but also to the environment. And those are the three evolving levels of machine learning: self-adaptation, self-organization, and finally, self-awareness. So you can sort of think about this as sort of the evolution, if you will. Self-adaptation feeds into self-organization and self-awareness. Well, here we go. If you think about the evolution of computers and how they're used, and think about elephants. All right. What about gestation? The birth of an elephant. It's about 2 years. How about the gestation of a solution using a computer? Yeah, problem formulation might take hours. How about training? Well, here's mama elephant and there's baby elephant. Training for an elephant, about 3 years of training. Or computer solution, well, you got to test that thing and you got to apply it. Your computer grinding time might be anything from a few hours of computer time to grinding through the data to perhaps a few weeks. And then finally, motherhood. And in motherhood, elephants don't expect genius, so neither should you. And that's really the bottom line. There's no magic bullet, there's no golden arrow in any of the machine learning solutions that you think about. But it helps us to work on a new level. There's a difference between artificial intelligence and machine learning. AI attempts to mimic operation of the human mind. How does it do that? Well, by encoding the procedures and adapting to the environment. But machine learning is only a subset of artificial intelligence. It adapts to the data, but it is not adapting to the environment. There's a third thing here that's probably worth discussing. You may have AI and machine learning as ML. There's a third thing called reinforcement learning, RL. Reinforcement learning learns by adapting to an environment. That's reinforcement learning. And we'll take a look at reinforcement learning and how that relates to things. I want to draw your attention to something a little bit different from the first three. A new term, semi-supervised learning. Well, what is that? Well, that's where you come in. It blends a scientific judgment with several machine learning algorithms to develop a hand-tooled, reasoned analysis for making better predictions. That's the bottom line. We may use machine learning, reinforcement learning, adapting to an environment, but it is guided by us. It's semi-supervised using a variety of tools. Now, fortunately, in our industry, there's some early work that goes all the way back. Machine learning was not a last-minute discovery by the upstream oil and gas business. No, not at all. Terry Tanner and Sven Treitel published in the 2004 SEG convention some very interesting results. The title of their presentation is called Listening to the Waves. And over here on the left is a conventional amplitude display. The Zechstein evaporate is down here. And if you look on the right, this is a very, very early attempt of using machine learning to classify the seismic patterns seen in the data, like the left over here. I mean, certainly you can see the unconformity. Cutting through here, we see different patterns from the sea bottom down to about 600 mils. We have one reflection pattern, and below this parent anticline or nose of anticline, we see a different reflection pattern than an unconformity. Then we see a couple. It's very interesting, but you can see on the left a series of patterns. And look over here on the right. We have color-coded here one of the early machine learning analysis. And the analysis is that for every seismic sample that we have over here on the left on this section, we have a seismic sample on the right, and it's a machine learning classification. Now, the classification are color-coded, and they're not really based on picked wavelets. For example, if you're just getting started in this machine learning stuff, you think about, well, look, I've got a flooding surface here at about 700 mils. I'm going to run my auto picker across this thing. I'll have the picked amplitude as well as the picked time. And I'll have another one down here, and then a third one. You know, you have a series of horizons with horizon properties and interval properties, for example. But that's not what we're looking over here on the right. This is classification of patterns. So even within the space between the horizons, of course, we have continuous patterns of seismic data. So they're not, on the right here, they're not picked wavelets in any sense of that. And it's a much finer detail than any reflection wavelet itself. Because if you look at the samples over here, yes, it's crude and ugly and things like that, but it's a step in the right direction. It's not using the properties of the picked wavelet. It's using properties, attribute properties of the data itself. So if you're familiar with single trace attributes, you might actually recognize that these are wavelet properties. And Terry Tanner, I believe, was the author of the concept of wavelet properties. All right, I'd like to have a little mind game with you, if you don't mind. Let's take a look at an example of machine learning. And it's machine learning in the sense of self-adaptation. So take a look at the picture over here on the left. And this is a fish factory. And let's pretend for a minute here that your uncle from Alaska, from Dutch Harbor, Alaska, in the Aleutian chain, for example. Your uncle had a fish factory up there and he passed away, and he willed his fish factory to you. Interestingly enough, you have just recently graduated from Stanford. And what? Your degree is in data science. And you ask yourself, well, I'm getting uncle's fish factory. Is there any way that I can kind of automate this process? Well, what would you do? You could place sensors on the conveyor belt to measure fish properties, couldn't you? You see, we got all these people lining up here, and they're grabbing a fish, and maybe these first four are to pick up cod, and the next is to pick up an eels, and the others pick up halibut or something rather like that. Who knows what's going to come through? There's going to be some trash fish. Is there anything we can do to automate this? Well, here's what you can do. You could place sensors on the conveyor belt to measure the fish properties, couldn't you? Now you have to do this one at a time, not quite this big, but you run these through, and let's say you have a bucket of cod, for example, and you run that through the conveyor, and you measure some statistical properties of that type of fish. And then you have another bucket of something else. You run it through, and you're measuring for each of the classes, you're measuring a series of statistical properties. Not all going to be the same. You've got young ones, old ones, and through their life, their textures change, their shape and their size change, their weight changes, things like that. So you could make a spreadsheet for each of these types, each of these sets of measurements for each fish. And each of these measurements that you make would be an attribute of each of the classified fish. You would set up a machine learning algorithm with a neural network. And you would have it train on these buckets of fish, one bucket of fish at a time. And it would train with the neural network, and the neurons would adapt to the type of fish that was going through, and you would train the algorithm on the spreadsheet of the fish. Now you could either use a spreadsheet, or you literally could run those fish through there again if you wanted to, but let's make things simple, and we'll just apply the algorithm to a spreadsheet. Then we hook up the neural network after we've got this thing trained. We hook up the neural network that's trained now, and we're going to now classify fish one at a time. And at the end of the training period, a little further along on the conveyor belt, we have a separator switch at the top of the conveyor, and then it's going to divert the fish into one bucket, saying, we found this is an eel, and we found this is a cod, this is a halibut, that sort of thing. That's how it works. Now, there's nothing more sophisticated about machine learning than that. Honest, Pete, there really isn't. There is a fish factory use of machine learning. Of course, it's very simple. But let's not stop there. Let's consider that you have brought automation to Alaska. Good for you. But did you fire most of these fish sorters? Reasoning that you've just automated this factory and you only need maybe a couple janitors to clean up the fish scales. Everything's been automated. Maybe you need one or two experts in this line here, really good at finding the funny fish, the oddball things that the machine learning can't handle. But I ask you and I challenge you, aren't all the people on this line experts? Can we consider doing something other than firing? Consider expanding the operation to keep all the sorters busy? For the following. Can you retrain some of the low-achieving fish sorters to do other jobs? And we would call this social responsibility. It's a win-win situation. We are using machine learning as a tool. We are taking some of the things that were done manually and replacing them, now letting the machine do it. It doesn't mean that we need to put everybody on the street with a tin cup. No. What it means is that they can move on. Now the tools have replaced what was done by hand, and now they can move on to bigger and better things, and hopefully not so much drudgery as working in a fish factory. Well, that's what it's really all about. Let's move a little closer to home now, and we're going to consider two big things here. One is machine learning for classification, which is when I'm sure you've heard about that. Machine learning for regression is something a little bit different. Let me kind of describe that. Now, I got this slide, interestingly enough, from a biology link, and classification for them is described this way. Let's say we're going to classify these people, and at the end of the classification, we find the ones in red are disease labeled, and the ones that are blue, those are healthy people. And we link this all the way back to a couple of genes, for example, gene 1 and gene 2, so that even with two properties here, gene 1 and gene 2, and the labeled results, we now can classify people as being either healthy or not. Now, mathematically, we would write this the following. We would say that we have a vector here, if you will, a sample of a measurement of somebody, and we're going to classify them into N classifications. In this case, N is 2. They're either going to be healthy or they're not going to be diseased. And that's the result. That's the classification. And the set of all of those classifications, that is the result of the classification itself. So X is classified to Y. Nothing fancy, nothing profound, nothing sophisticated there. Regression, however, is something a little bit different. In regression, we have already classified the healthy people. And now we find for gene 1, for example, that we can relate gene 1 of healthy people, not all people, but just the healthy ones. We can relate that to finding a trend, a regression property, if you will, that of a certain property of gene 1, that their survival rate goes up. This is the fundamental difference between classification and regression. And you might say to yourself, okay, yeah, that's fine, that's biology. Well, what does that have to do with finding a little oil and gas? Well, I just doctored up the slide here a little bit for you. And rather than disease and healthy for classifications, we're going to say it's a reservoir rocks, and it's either no pay or pay. Okay. It's either going to make us some money or it's not. It's either no pay in red, or the blue samples are going to be, yep, this is the good stuff. All right. So in the classification process, we might have seismic attribute 1 and seismic attribute 2, and these are the pay samples and these are the no pay samples. We haven't really changed anything. Our input seismic sample of 2 attributes or 20 attributes, whatever. We're just looking at 2 of them here. And then we have N classes, and then the resulting set, our results then are to break this up into are classified samples of everything. Every sample we've got is either going to be pay or no pay. That's the good stuff. This is an example of classification, example of regression. How do we translate that? Now we take all the pay samples, and now we look at the pay samples alone, and we are going to have a regression situation here where we can take some properties of the pay samples and we predict production. Now the property combination may be nice and linear. So we see that there's a trend going on here, and it's maybe a simple combination of attributes, which gives us then our ability to use a series of attributes and properties of X of the good stuff to predict production. But quite often it's not a linear trend. The property combination is not necessarily linear. It might be nonlinear. But nevertheless, if we can get to the point where we can start to predict not only which are going to be the pay and no pay, but also predict the quality of the pay, that's a regression problem. You with me? Not that difficult. Okay, and we're going to end up this presentation. I'll show you an example of machine learning regression, which is kind of interesting. All right, still at 50,000 feet, we're going to look at the different kinds of machine learning. The important concept here is that every machine learning algorithm, got that? Every machine learning algorithm is based on a model, a statistical model. Absolutely critical, absolutely fundamental. If you think about that, every time you hit the button to do some machine learning calculations, which are adapting to the data, the result is a statistical model. You may not want to think about it that way, but I urge you to start thinking about it that way. Every machine learning algorithm that gets run on the data, the result is a statistical model. Now, supervised learning needs to start off with training data. Unsupervised learning simply adapts to the characteristics of the data. Reinforcement learning adapts to the behavior of the environment. And finally, deep learning is some recipes of setting up layers of neural networks for classification purposes. That's how deep learning is used in our industry so far. And you might think to yourself, oh, well, we're very sophisticated people. We do deep learning, and we're really big shots, and we can burn through lots of electricity for our very sophisticated calculations. Well, hold on here. Down at the bottom here, let's take a look at this $270 algorithm, if you will, that's embedded in this little black box down here that goes around and sweeps your floors. This is machine learning, of course, and you may have bought one. It's US $270 now. Is this an example of self-adaptation, or is this self-organization, or self-awareness? Well, this is pretty cool stuff, because the little robot comes out from its charging station and it sweeps up all the dust bunnies along the corner. It knows that it can't go under everything, but if it can get underneath something, it cleans underneath the sofas and the chairs and things like that. And it also knows that it's not going to get stuck by getting jammed underneath the chair legs and things like that. Only $270. So let's not think that when we're blowing through a lot of money to apply machine learning that we've got something very sophisticated here. Here's a $270 example of machine learning that does self-awareness. Okay, self-awareness. The roles in our evolving way of doing business, of interpretation, geoscience interpretation, our roles are changing. If you're a geoscientist, your goal will be to learn how to use machine learning to interpret our data. Rocky Roden's presentation yesterday highlighted this point. As well, he pointed out reinforcement learning. Very important that geoscientists, quote, get on the bandwagon, and the goal is to learn how to use machine learning effectively as tools to help us interpret data. Data science, is there roles for them? Of course there is. Now, who is a data scientist? General practitioner of machine learning. And who's learning about our data right now and learning how to squeeze some value out of it. So should we just fire all the geoscientists and replace them with data scientists? Well, hold on here. let's just let's keep that one up in the air right now for a little while. But we'll have some thoughts later on. It's not a really contest here between the geoscientists and the data scientists. Now, there's a third group here, the IT specialists. They understand the data silos. Every company's got data silos, those specialist data, like our upstream oil and gas data, how we carry around our logs, how we carry around our seismic data. Those are specialist data silos. And those need to give way to transparent access of the library, or a library of big data. And Schlumberger, their Gaia initiative, has spent a lot of effort, a lot of blood, sweat, and tears to help overcome these limitations and get data out of the silos. Has made that commercially available. If you're an Exxon, if you're a Chevron, or if you're a Shell, or any of the other ones, you have worldwide data that goes back years. And so the Schlumberger Gaia solution is an opportunity. Or perhaps you may decide that you just want to keep stuff in-house, and your IT specialist, I'm sure that one of their goals is to figure out how to get the data out of the silos, make it available, make it transparent access across the company, and certainly preserve the confidentiality of the data. And then software developers, well, hello, you better realize that machine learning is here to stay. It's not going to go away. And you need to resolve to learn how to apply it. And I think by this point, you probably see that I really think that we need all four. Teamwork, cooperation is very important. By the way, if you think that you've figured all this stuff out, your little doodle down here was to connect each of these four within your company. Who's your favorite geoscientist, and what would be the best icon for your favorite geoscientist, your face, the software developer. And by the way, if you are a fan of A Hitchhiker's Guide to the Galaxy, this is a Vogon. What is a neural network? In machine learning, what is it? Well, it's the repository of the data characteristics that have been learned from a set of training data. That's all it is. That's what a neural network is. It's the repository of the data characteristics. It's like the computer brain, if you will. But you train on different data, you're going to have a different neural network after training. So you need to preserve the results after training, because that then becomes something that has been adapted to for a particular type of data, and that's got some value. Now, in the computer, the artificial neural network is nothing more than a computer network, if you will, of adjustable weights and connections between weight points. Now, these connections serve as a simplified version of a real brain. In this case here, we've got two eyes, and the visual cortex are on the back of the brain, and you can see how they cross over. What do our machine learning brains look like? Well, hello, yeah, they are brains too, but they're child's play by comparison. Let's realize that the human brain is a product of many, literally billions of years of evolution. So we have plenty of time to try to get it right. And even today, our brains are not perfect. It's still in the process of evolution. Well, here's a couple ridiculously simple-minded machine learning topologies, if you will, and topology spaces. And I've called topology spaces for an important reason. Different neural networks for different characteristics and different requirements and jobs that they're to do. One of the early ones was called a multi-layer perceptron, and this is what it looks like. You've got, in this case, 4 inputs that come in. You feed in one sample of data, and it's got 4 values. It goes through the multi-layer perceptron. In this case, there's 1 hidden layer, and the result is a single output. So based upon these 4 inputs, it reduces it to 1 output that we would call classification. Autoencoders do something slightly different. Here's an input that gets reduced by a series of layers of neural networks. We have an encoding stage where we reduce the dimensionality from these many input numbers to this level right here. This is called the code. And then from code, then it is decoded back to an output, which gives us the result. So these are called autoencoders, involved in 2 stages. There's a data dimensionality reduction and an enlargement after the end. Convolutional neural networks are specialized in the sense is that you have an input, and we have a whole series of convolutional layers. This is an example of one layer, a sigmoid activation function, and then a pooling layer right here. So the convolutional neural network is a combination of specialized layers, and these layers are connected. Excuse me. Topology is another example of a topology space, and we have deep learning. This is an example of deep learning topology of a number of hidden layers, and the layers have specific tasks. The result is starting from the input pattern of the data, going through a series of layers, and then the result is an identification, classification of it's either solved or it's non-solved, for example. Reinforcement learning operates a little bit differently. Yes, there is an environment, and the interpreter is the I, which offers to an agent a reward for good behavior or not, and only rewarding an agent for an improved state. So based upon the agent going back to the environment with a new action, and then goes back to the interpreter with a new state of the agent, and the agent is either rewarded or not, but it goes back. And this is a continuous process of adapting to the environment. If the environment never changes, then the agent eventually, the rewards drop to 0 because it's then fully trained. If the environment is changing, it can adapt to change as well. And then deep learning topology, which incorporates not only classification, but also it has not only an encoder stage, but a decoder stage. And that would then take it back to identifying a classification problem in this case. All those are examples of machine learning brains, if you will. Those are the neural networks. I'd like to move on to another topic here, and for a very good reason, as you'll see in a second here. This is the Shazam story. Shazam. You get a little app for your smartphone, and you have it listen to a few bars of the music, and Shazam tells you what's the name of the song, who sang it, and when it was sung, and oh, by the way, would you like to buy a copy of it? Okay, so that's how they paid for the whole business. It was founded in 1999, acquired by Apple in 2018. The reported was $400 million. That's a lot of money. Well, yeah, but when it got started in 1999, that's 19 years later of working out all the gory details. Apple cherry-picked it, literally cherry-picked it 19 years later for $400 million. So what they're doing is they paid for all that effort, the blood, sweat, and tears that was put into finally a product that has some general appeal. They worked out all the bugs. They made it cool and made it work. And it's a lot of work. And Apple picked it up for $400 million. Now, the nice thing about this Shazam application, it's machine learning. It not only recognizes authors and publishers, but also the artists, and does that at lightning speed. The whole 19 years of effort was developed at lightning speed because the people that were doing the development realized that others had the same idea. And if they didn't get there first, somebody else is going to get there first. They're going to get the golden chest. Now, how do they do this? Well, they use a spectrogram, which is an audio fingerprint, to match a database set of classifications. So just a simple spectrogram of the music itself. And it now offers selections. Hey, you want to purchase this thing? Or do you want to buy a whole album? Or do you want to add this to your custom playlist? That kind of stuff. All right. And the paid options also go on into TV recognition. You got a picture of your favorite actor who was in a series in the 1950s and hit the button. And it also now does TV recognition. And it also allows you to chit chat with friends because it's hooked up now with social network. So now you've found something and you can share it with some friends. And it also offers services to iTunes, Spotify, YouTube, and Groove Music. Very, very interesting story. This is a circuit this year of this year, and this is where that thing is gone with the blood, sweat, and tears of 400 million, and then Apple takes it from that point, and everybody wins because the founders and the people that worked for those 19 years, they got the 400 million. And maybe some of them got some jobs at Apple, and then Apple wins because it takes that and integrates it with all the other wonderful things that they have for their the Apple phones. Next gear, let's take a look at machine learning. Now that you can appreciate kind of the benefit financially of machine learning in other areas, let's take a look at machine learning in its barest bones. Okay, it's the following. You can organize the data logically in a spreadsheet. It's as simple as that. We have n samples. So row 2 here is sample 1. The next is sample 3, da, da, da. We have n samples. And for every sample, we have m characteristics. Number of characteristics is m. And this could be seismic attributes. Those could be flow rates of the reservoir, Young's modulus, whatever you want. Whatever you're adding here, those are the columns. It's a simple spreadsheet. Every row is a sample. Every column is a property or an attribute. So let's compare supervised machine learning, which is self-adaptation. And how does that operate? Well, it operates as the following. We have our spreadsheet here, n samples, m attributes per sample. And we go through a training step. And based upon these training samples right here, the neural network weights adapt themselves, and they go through a number of training and retraining, adjusting weights, try it again, try it again, try it again, try it again. Finally, things don't change so much. And what we're doing is looking at the classifications and looking at how good the classifications are going to be estimated from the known classifications. Because we're starting off with training samples here, and in the training step, we know what the classifications of sample 1 are through sample n. We know what the right classifications are. And the neural network, by training, is estimating the classifications, adjusting the weights. So we can compare the estimated classification of every training sample with the known value. And it's based upon that, whether you have it correctly answered or you didn't make it, these are not all perfectly matching the known classes. We already knew what the training sample classifications were before we got started, but we went through the neural network supervised machine learning because we already knew the classifications of the training data. And after we're done, the neural network is fully trained now. Now we can go through a second step. This is the classification step. And we can bring in additional samples or other samples, or maybe the original training samples and a bunch of others. And these are all treated as unclassified samples now. And we run it through the algorithm. And we now have a classification of these samples. So the ones here at the bottom of the classification step, these, and the way we got it shown here, these are untrained. We don't know what the real classification is, but we do classify them using the machine learning, which has adapted itself to the, in the training step, adapted to the properties of the training samples. Unsupervised self-organization, a little bit different. We have training samples, but we don't have any labels. We end up with a classification. And so now this is a fully trained, self-organized, unsupervised classifications, a set of classifications. And the classification step is to take some other data run it through and we classify those. So what's the difference between classified and unclassified? I'm going to back up. That's supervised. That's unsupervised. Hello? Is there that much difference? Really? The only difference is in unsupervised, we don't have the classes. This is supervised. This is unsupervised. Supervised, we have training samples and we know what the right answers are. And unsupervised, we don't. So that's all there is, all the difference between supervised and unsupervised. Deep learning, we have massively parallel neural networks with many hidden layers, and we have feature reductions, and we end up with a classification problem where we have a set of training samples. We have some pictures of doggies and raccoons and kitties and things like that, and we end up classifying them. These are the training data. We know what these critters are, and then we can look at the error of the results of a fully trained set of deep learning, machine learning example. And then now we've got a brand new sample after it's done training, and we run that through and we say, yep, it was a kitty, and we did some good job. So the steps are massively parallel neural networks, recursive machine learning steps. They could be both supervised and unsupervised training components in the hidden layers. It all depends upon the recipes, a mixture of components that are in the deep learning example. And the training decisions are hidden because you don't see what's going on inside here. You just have an input sample and you see the output sample. So that is not an example of self-organization. It's an example of self-adaptation. Okay, now I'd like to now move on to tuning thickness. If you have a classical geophysical training, you're probably pretty well aware of tuning thickness. And a lot of practicing geologists know what tuning thickness is. Excuse me for a second. So we know that tuning thickness is the limitation, kind of like the end of the limit, the lowest, smallest thickness that we can resolve with our seismic data. So a classical wedge model, we have a symmetric reflection wavelet that's based upon our survey. And we have only top of the wedge, bottom of the wedge, and we get this time separation. And the next trace over, the thickness is a little bit less. Finally it goes to zero, and we end up with a dead trace over on the far right. And if we go from low acoustic impedance to high and then back to low, we have a symmetric peak event and a symmetric trough event. We eventually get to tuning thickness where the amplitude starts to interfere so that the peak interferes with the trough of the reflection from the bottom and builds up the amplitude. So we have then, at tuning thickness, we don't have a symmetric reflection event anymore. It's now anti-symmetric. It's a peak followed by a single trough, peak trough. And we define tuning thickness as that trace of that critical thickness of the time layer of that wedge at which the amplitude is the largest. Let's take a look at tuning thickness and see what relates to what. I've got two tuning thicknesses right here. For this reflection wavelet right there, our tuning thickness is 8 milliseconds, maximum buildup of amplitude. So if we run the auto picker on the peak, we run the auto picker on the trough, and we look at those properties, we look at the time interval, we look at the amplitudes, track those two for examples. The red curve is our amplitude curve, auto picked, and we see right here at 8 milliseconds, that is the maximum buildup of amplitude. And then it eventually settles down, if you will. Now, I didn't mean to confuse you on this, but these are backwards, okay? Because what we have here, this is the thickest to the thinnest. and the thinnest to the thickest. Sorry about that. I have them reversed. My point here is to help you see that the wavelet has a profound effect on tuning thickness. If we were to look at tuning thickness of 8 mils, and our limitation is maybe, I don't know, maybe half or possibly 2/3 of tuning thickness is our limit. Well, that's much better, higher resolution than the one for 28 mils, things like that. And if we carry this stuff a little bit further, there's a number of other properties that we can record from this model right here. And if we start with this, we have a black curve, a red curve, and a green curve. Black curve is the frequency spectrum, frequency from 0 to Nyquist frequency here. And we have the peak frequency, which is red, of the signal. The black is the total peak frequency for everything. And then the signal to noise ratio is the green curve over here with the scale on the right. Now, based upon what we record, we also have the tuning thickness chart, and we have the frequencies, and we have the basic wavelet. From that, if we replot the data in the frequency domain, replot that in decibel scale, pardon me, we would have it at a 30 dB down point here, this bandwidth. Okay, so these are all numbers that could be part of our model. Tuning thickness chart gives us the tuning thickness. It gives us a peak frequency. It gives us a bandwidth from F1 to F2 at, say, a 30 dB down point. And it also gives us a peak signal to noise ratio. So you see, with a little model here, the only thing we needed to have was just be a captured wavelet and made a zero phase assumption, and then we get 1, 2, 3, 4, 5, a bunch of pieces of information about that reflection limitation. We also have not only the peak signal noise, but the peak signal noise frequency and the amplitude excess. Because at tuning frequency, the amplitude is a little bit higher, and then back here, it settles back down to, say, unity. So it goes from 1 to, say, a 1.2 or 1.24, something or other like that. It'd be a 24% excess amplitude buildup just due to tuning effects. All right, so we're going to take this, and then we're going to look at this captured over 20 3D surveys around the world. And these are some of the results of capturing this information, statistically estimating the amplitude spectrum and the signal spectrum from the data. And these are some of the results. This is tuning thickness on the left and the frequency bandwidth on the horizontal axis. And we can see for these 20 surveys here that there is a trend. And in fact, the trend shows is that as the bandwidth increases, tuning thickness trend decreases. Hello, this is regression, isn't it? Look at that. That as you get more bandwidth, if it goes up to 80 hertz bandwidth, 90 hertz bandwidth, tuning thickness goes down. Well, this is just captured from the real data itself. There's no theoretical model here. This is just based upon the wavelet itself and a simple model of a wedge model run over 20 3D surveys around the world. And we can see a nice trend there. Let's look at some others. How about tuning thickness amplitude excess? Maybe there was a 20% increase, or maybe there was a huge 50% increase in amplitude at tuning thickness. So here's tuning thickness again on the y-axis. Horizontal axis is amplitude excess. Can you make much of a pattern out of this? Can you say, well, I can see that over here, it's about 20 mils, and our tuning thickness amplitude excess is, well, it's nothing to take home about. So the point here is we can analyze these either 6 or 8 attributes of the wedge model, and then we can use these to do an analysis. And for this analysis, rather than 8, we're just going to drop this to 6 because there's quite a bit of redundancy here. We're just going to look at the bandwidth. Here's a spreadsheet. And we've taken the tuning thickness that we statistically drew just from the amplitude data alone, the frequency and signal, total amplitude spectrum and the signal amplitude spectrum, which we estimated by correlating adjacent traces. And we sorted this spreadsheet. So the best one was Rocky Mountain, US, and the worst was offshore West Africa. Gulf of Mexico's in here, Gulf Coast, North Sea, Northwest Territory in Canada. And these are the values. And based upon this, we're interested to find out which is the strongest correlation. What correlates with what? Now, tuning thickness, of course, correlates with itself. So if we organize this into a matrix, and we're going to compare tuning thickness with amplitude excess, tuning thickness with peak signal noise, and we look at all the strength of the correlations, and we would find the following. We would find that tuning thickness best correlates with bandwidth and with the peak frequency. Those are the best correlations. Other things are just not so good and not as strong in terms of correlation from the covariance matrix. So we're then going to take this data and we're going to subject it to unsupervised machine learning. And we've got the table now, but now we're organizing these into different groups. And I've color-coded these. We've run this in 3 different levels, if you will. And then we've organized this in terms of 2 classifications, 3 classifications, and 4 classifications. Now, what we're interested in here is for a 3D survey that had excellent tuning thickness limitations. Could nail it right down to 8 milliseconds for tuning thickness, which is a far better survey than this one for 16 mils, or this one here in the Gulf of Mexico, tuning thickness 28 mils. Now we're going to run this with unsupervised machine learning with a neural network of 2 classifications. So you see here, grays are classified as 1, and then the blues are classified as 2. So you've only got 2 classifications for these set of 3, 3 classifications for the next, and then 4 classifications for the rest. Now, interestingly enough, if you look at the 3 runs here, here was 1, and all of these classified in 1 group. And for 3 classifications, these 2 classified, these and this classified as 1 group. And then they broke out into furthermore. And then if you add 4, we find is that it gets a little bit more murky here. So we sort of have a hunch that by having only 2 classifications, that's not enough. 3 classifications maybe, and 4, I don't know, maybe too much. If we look at the results, we're most interested in where the best tuning thickness case is kind of our guide on where we want to go. So we're looking at 3 different initial conditions, and we're looking at 3 different neural networks. And we're going to select the best model by majority vote. And to do that, the best model of the smallest tuning thickness is 4 out of 5, and that is this one and this one and that one. Our best is model 3, where we had 3 breakdown, and it was the 3rd classification. That gave us the best results. Pardon me. So we would say that of all these 23D surveys, it is the classification of these attributes, of these 6 attributes, that gave us the best results. And if we look at the results, we're not going to take the time here to dwell into this too much, but I just want to show you the conclusions. Our most important attributes for the best statistical model was the largest signal frequency, which is component 5, and the largest bandwidth, which is component 4. Winning neuron 3 was the best. And if we think about that, our 3 different winning neurons is, remember we have 8 attributes here, or 6, depending upon how we ran this thing. And in this case where we ran it is the full 8, turned out that winning neuron 3 was the best. It had the smallest error. And that's based upon 20 data samples. I'd like to offer the following for you skeptics out there. You might not think that unsupervised machine learning is really the way to go. So I got a question for you. One of the issues of unsupervised machine learning is who's going to pick the attributes? Well, we would claim that we want to do it as geoscientists, geological bent, geophysical bent. We want to pick which attributes to use to run this machine learning. Now, you may say to yourself, I'm a hardcore individual and only orthogonal attributes tell the story about the nature of things. Okay. In other words, I know that if I have orthogonal things, that means is that they don't correlate with each other. If I've got 5 pieces of information and they're not correlating one with the other, well, that must be good because we're getting information through all, say, 5 channels. They're not correlating because they're separate pieces of information, different properties. That's orthogonal. Well, hello, if that's true, wouldn't it be true that you only need one geophone at the receiver station? Because truly, for a seismic trace, the only thing that you get out of that is the trace and its Hilbert transform, and those are perfectly orthogonal to each other. So you believe that? Do you believe that you really only need one geophone then? Well, nah, we obviously don't believe that's true. We believe in the power of stacking. We don't deploy one geophone, we deploy a whole geophone array at a station. So here's the point. In exactly the same way, stacking of multi-attribute samples, where every sample is now not just amplitude, but selected attributes that go along with it. They stack in attribute space, and they lead to natural clusters that can be picked up by machine learning. We had 8 attributes, 8-dimensional space, there was natural clustering, and we discovered that winning neuron 3 was the best result. So we use machine learning to identify the natural clusters of attribute combinations in high-dimensional space. We just can't see it. We cannot see anything in 8-dimensional space or 5-dimensional space. Hard enough in 2 or 3-dimensional space. So here's a little big important thing to remember, and that is we use machine learning to identify natural clusters of attribute combinations in this high-dimensional space that we can't see. With that, we're going to take a little bit of a break here. I've got 11:02, and let's take a 10-minute break. Laura, back to you.
Sure. Tom, do you want to take any questions before we break?
I think what we're going to do is take a break and hold your questions. And we're actually, I think the best thing to do will be to take these to the chat room where we can all kind of join in and have some fun with this stuff. And everybody gets to learn.
Very good, very good. Well, you guys go take a quick bio break or get a cup of coffee, and we'll see you back here in 10 minutes.
Thank you, everyone. See you in 10.
Okay, Tom, whenever you are ready, I think your microphone's gone on mute, so you're welcome to pick it up and get started again.
Okay, sorry. Laura, can you hear me now?
I can hear you just fine.
My mistake. Sorry, everybody. Okay, can you hook me back up?
Sure. We're seeing your screen. We're seeing the PowerPoint slides, the slide sorter view.
All right, good. All right. Well, I apologize, everyone. That cost us a few minutes. Mr. Moron couldn't find his mute button.
You're just
Please
fine.
forgive me.
Go ahead.
All right. All right. Let's continue on with some terminology, because these are fundamental concepts on helping understand how computer can adapt to the data, because that's what machine learning is all about. Well, here's three. Machine learning models. Well, what is that? A machine learning model is like you've got a deep learning set of hidden layers, and that is your neural network pattern. That is your machine learning model. So it explains the mechanism of taking a series of time steps to adapt to the data for the data adaptation. Iteration and recursion are slightly different. Iteration simply means, for example, like you've got a little intrinsic little operation that you can call, and it will return a random number for you between 0 and 1, for example. It's a random number generator. So you hit it again, you get a different random number between 0 and 1. And that's an iteration, just goes bing, 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 bing. And just repetition of a process, that's iteration. Recursion is something a little bit different. The output from one step becomes the input for the next. That's a recursion. And that's exactly what machine learning is all about. It's not iteration, it is a recursion. And the learning process is starting with your neural network at some set of weights, and the connections are already made. And then it's working, adjusting through the data through a series of recursive steps, time steps, and they really are time steps, by the way. It takes so many milliseconds, or who knows, so many hours to complete a single time step, and then it does it again and again and again. So it's a recursive process. All machine learning is recursion. Supervised and unsupervised learning. You either have training samples to begin with or labels on the data, or you don't. Supervised, unsupervised. Training and classification, there's a distinction there. Training is where you're training the neural network. Once it's fully trained and you've got the best you can get, can't get any better than that, your training is done. And then we go to classification, and we got some wild samples that are coming in that are brand new to us. And we're going to apply the trained neural network to these new set of samples. That's the classification process. Dimensionality reduction is an important concept. It's almost as important as recursion, because in dimensionality reduction, what we're doing is going through a series of layers, and the dimensions are reducing to distill the data characteristics from a higher dimension to a slightly lower dimension, and then from a slightly lower dimension, lower still. We're distilling common data characteristics. There's a thing called the objective function, and that's generally like the steering mechanism in a sailboat, if you will. The objective function is our measure of how we're doing, and compared with the last epoch, which would be the last training step, the objective function is at reducing error. Are we getting better or are we not? So that's called the objective function. How do we take an error reducing training step? That's the objective function. How do we take one training step to the next? Hyperspace is the training sample is in hyperspace. If you got 8 attributes, it's 8-dimensional space. If you got 3 attributes, it's 3-dimensional space. Multi-attribute of 3D seismic survey, every time or depth sample is not just the amplitude alone, but it's the additional set of attributes that you're using with it. Maybe it's a texture attribute, or maybe it's a instantaneous frequency or an envelope, or whatever you're using. You're attaching so that at that seismic sample, it's no longer just a single value, it's a little vector, if you will, a vector of, say, 8 properties, 8 attributes. There's a thing called the curse of dimensionality and no free lunch theorem, and every self-respecting machine learning person needs to sort of get comfortable with this, because you can be sure that your data scientist is going to throw this at you, and you better be ready. Curse of dimensionality, what in the world is that? Well, as you get into higher dimension, space grows sparse. Okay, I know, this is like Star Trek. Even as the dimensions grow larger and larger and larger, space itself grows sparse. That seems pretty odd, doesn't it? We're familiar with 3-dimensional space. We know we've got like the Euclidean distance from my nose to my finger. No matter where I move my finger around, I can calculate the distance. Well, think about how you have distance when you've got 4 dimensions or 5, or maybe 100 dimensions. Space itself, the whole concept of the spacing between samples, grows sparse. That was mathematically shown, I don't know, some time ago, quite a long time ago. And altogether, that's called the curse of dimensionality. When you increase the dimensionality of your problem, it's a curse, because space grows more sparse. The distance between your samples grows larger, larger, and larger. And trying to identify natural clusters of information is to be more difficult. Okay, the second big concept is the no free lunch theorem. And that's an interesting name for something, just like curse dimensionality. I think you'll easily remember the name of these things. No free lunch theorem means the following. In a nutshell, if everything is equal, nonlinear optimizations cancel themselves out. If you've got a fancy nonlinear way of doing machine learning, and it works just really awesome on this particular data, and it's just wonderful. You got a different set of data, and maybe the results won't be quite so good. And maybe other cases, it's a little bit better. All your nonlinear optimizations that you have to try to speed up the process, if you keep applying that for different data, keeping, of course, the attributes the same, all things being equal, the optimization cancels itself out. That's called the no free lunch theorem. I'm going to show you a little example of that as we go on. Now let's take a look at Lena. Okay, this is a picture of Lena. Lena is very famous in image processing. Lena is, well, I think Lena is probably getting a little more middle-aged now. She is a Swedish model. They took her picture, and she's probably the most photographed model in the world. Why? Because she's a this picture is a digital image that's been used to calibrate literally every photographic application ever created by human beings, ever written. So this picture, believe it or not, Lena, is like a test picture, right? And it gets applied everywhere. Well, what in the world is Lena, the picture Lena? Well, we know that it boils down to a whole series of pixels, so many rows by so many columns, picture of Lena, and every pixel is a color, of course. If it's in the middle of her eye, the nose, her lips, the hat, the background, okay. Every pixel is a color, a red, green, blue color. Now the picture may have 512 by 512 pixels, but each pixel has a value of red, a value of green, and a value of blue, okay? If it's red, the value of red is 255 and then 00 for green and blue. That's pure red. Green is 0, 255, and back to 0. Blue, as you can see, 00, 255. White's everything turned on. So what we have here then is 3 8-bit bytes go together to give us that color. So what is Lena? Well, Lena is this picture right here, right? So what we have here is the very first pixel, all right, with these red, green, and blue colors for 1 pixel. And that's like the first dimension for that pixel. And then we've got another color value for the next pixel. And so for every pixel here, Lena is sitting in a dimensional space of 512 times 512. That is exactly what Lena is. If you change 1 pixel in any way, yeah, that's no longer Lena, it's something else. So pictures, interestingly enough, pictures are messages. Now we may choose to have characters like ASCII character sets. When I write TEXT, you know, that's an 8-bit character and another 8-bit character. Now we can have a color like Lena, or we can have just a text as a color, but each of these are messages. The color model may be red, green, and blue, hue, saturation, and intensity, and C and Y, whatever that is, I've forgotten. They all describe the color digits in a picture message. So all this boils down to different kinds of messages. The messages are all similar, and each message is like a single point. Each picture, each text file is like a single point in hyperspace. Yeah, it's high, but we're going to use machine learning to search through these patterns in hyperspace for characteristics. We're going to try to identify natural clusters of similar pictures, similar Word documents. Maybe there's some key words that were used, or maybe there's some particular characters. We're looking through this very high dimensionality space for common properties. Now, we may label Lena as 1 point in this hyperspace. So training is nothing more, excuse me, for training our neural network to try to identify Lena. And there's many different kinds. We have text messages, pictures, we have multi-attribute seismic surveys. All these are examples of different hyperspaces, if you will, of different dimensions. But the whole point here is, and this is why we put a gold cup on this message right here, this is something worth remembering, is that once a message is defined, it is a single point in hyperspace. Single point. So Lena is a single point in hyperspace. The baboon is a single point. This text file, they're all different points. A sample in a 3D survey is a single point in a hyperspace. The messages all reside in the hyperspace. So if we have m bytes long, it's like at the corner of an m-dimensional hypercube. Say, we're just going to take a look at something real simple here. Let's say we got hello world. We've got a letter H, an E, an L, L-O, and a space, and WRLD, exclamation point. Each one of these is a certain position in an ASCII table. We say hello world, we've got 12 characters, we've got 12 bytes right there. Each one of those is taken from a standard ASCII character set of 128 possible characters. Well, if we say HEL is the beginning of our word, 3 characters, those 3 characters, there's a possibility of over 2 million possible different messages as an individual point. When we just get to HEL, that's possible different location of over 2 million points. So when we say H is in the ASCII table, it's between 0 and 255, so it's H. And then we say HE. So HE takes us along this axis, again with the same ASCII character set, and that's an E. And then an L is our third letter. And you can see here, it's just adding these 3 little vector components together, and that gives you a point in hyperspace. So the message is nothing more than the values, and each of these are vector components. The H was the 8th character in the ASCII set that starts with the capital letter A through Z, and then the lowercase a through Z, and then the numbers and some funny characters and stuff like that. 255 characters in the ASCII table, things like that. So every message that we have is a vector, and it's a point in hyperspace, and that's what gets analyzed. Let's take a look at a situation here in cell biology. We take a look at our microscope and we take some snapshots. We got some raw images of some cells, for example, and we take the image and then we look at those things and we train them. We say, well, look, this is background. I'm taking my little blue brush and I'm drawing it through here, and those are examples of pixels that are background, and the interface is indicated here. Don't ask me what interface is. And then metaphase is something else. So in other words, a biologist will know the interface and metaphases. I got background figured out. But anyway, we go through a whole series of raw images and we train them. And based upon this, we will end up with a prediction of the pixel classes. These are metaphase trained, these are interface trained, and these are background. Okay. Now that's just one way of taking the raw image and using machine learning to identify these 3 classes: background, interface, and metaphase. Okay. Well, that's not the only thing that you can do. You can take the raw image and segment it. It's called segmentation. It's just an algorithm which identifies what most of the background color is. And then when you go from background to something else, you have an edge, okay? This is a segmentation process. Another thing that you could do slightly differently would take the raw images here and you just rasterize the things. You say, I'm going to take little blocks that are, say, 5 pixels by 5 pixels. You just rasterize that thing. And then you're going to look at different groups of those. It's almost like a little texture pattern thing. And we would go through a segmentation. We'd end up then predicting the object classes, and if we use rasterization, we'd end up with raster classes and things like that. You see the sort of flexibility that you have here? There's just a lot of things that you can do using machine learning. And the point here is that it's nice, but it's incomplete, because you've got the stuff done, but where's the quantitative comparison of the results? What is the statistical model that you're using here? That's really the important thing. So if you are going to be a user of this machine learning stuff, please take the time to understand what's inside the black box. For this one, for example, this is a supervised learning, isn't it? You got out your little paintbrush and you drew this, and you said you did some classifications. Next one, using segmentation, was based upon identifying after the segmentation of just hitting a dot, you say this one's interphase, and this one is also interphase, and this one over here is a metaphase. Pardon me. That speeds up the process, but the end result here again is a prediction. And the raster sort of process goes through the same thing. Please don't assume that if the computer did it, it's got to be right. Don't assume that, please. All right, we want to shift gears a little bit here and talk about, help introduce you to the concept of hard and soft attribute spaces. And you might think, oh, well, if we're going to have a hyperspace here, it's all the same, isn't it? Nah, not really. We can generally classify these spaces, hyperspaces, as hard or soft, and they're attribute spaces, of course. So across the top here, these are some examples of hard attribute spaces. Let's say we've got a large physical experiment going on here, and it runs for 5 days, and we've got 8 instruments hooked up. And during this process, we're taking measurements all the way along. Many captured variables, large physical experiment. Or we have a large mathematical model, but we have some unknown regions of interactions of this mathematical model. And we just want to run this mathematical model, and we want to observe how it behaves. Those are both examples of hard attribute spaces. Soft attribute spaces, a little bit different. If you want to study the COVID-19 pandemic, you want to find out, for example, as why do the people in Kuala Lumpur, why is their catching the COVID-19 rate different than Cairo, Egypt, for example? Or you want to find out what's going on in Calgary, Alberta, that sort of thing. You want to study the properties of the pandemic. Many variables, but you have imprecise measurements. Not hard, imprecise. You're either sick or you're not. You either died or you didn't. Well, that's about as far as you can go. And there's a lot of extenuating circumstances and decisions by hospitals and things like that. You get the idea? Those are softer attribute spaces. Or you want to study the world's economy. What are the factors? You want to make some money? Study the world's economic factors to try to predict business trends. Clearly, that's another example of soft attribute spaces. How do you study these things? Well, there's this concept of digital twinning. And what it is a digital twin is a mathematical model of something physical. Here's some examples of some digital twins. Alfred E. Newman and a digital twin of Alfred E. Newman. Alfred E. Newman and another variety of Alfred E. Newman. And here's the third one. These are examples of digital twins. In the case of seismic vessels, for example, yeah, you can actually model how with the mathematical model of the hull of a ship and the weight distribution and everything else, you can model how it's going to behave in seas, different sea states, for example. Airplanes do the same thing here. You have a digital twin, a mathematical model of a real airplane. You don't have to go out, for $18,000 an hour, go fly the airplane. You can just fly the digital twin. Same thing for the human mind. Got it? Easy. You might say to yourself, well, look, all our stuff is our hard attribute machine learning problems. Oh, really? Well, let's think about that. Here's one that definitely is a hard attribute machine learning problem. You got a bunch of earthquakes. And for one earthquake, we have different stations that we record the response. And from that, we can capture a mathematical model to try to model what our data were by adjusting the parameters. That is an example of using machine learning, the mathematical model, that's the digital twin, to try to model the earthquake prediction. It's a hard attribute machine learning problem. Now let's move on a little bit here and compare classical inversion with machine learning recursion. Are they the same? Nah, not really. Are they fundamentally different? Nah, not really. What are the differences? Well, if we're going to do inversion, we're going to try to model the subsurface. So we'll have model properties, And from those, we generate model traces, and we compare those with our seismic. This is the Earth. This is our model of the Earth. We will mathematically tweak the model parameters here, and then generate model traces again, and again compare those with the real world, and then we'll do it again. So we're going through a series of iterations, tweaking the mathematical model to refine the mathematical model to match what's going on with our seismic data. That's an iterative process. A recursive process is to have a model set of properties, a model trace, and then from these, we have compare those with the seismic data, mathematical tweaks, but the output from the first one becomes an adjustment for the second one, and then it goes on and on and on. Our computer process is to minimize the model error, okay? Here, the computer is training error is what is being minimized. So in seismic conversion, we estimate the rock properties using a mathematical model that's fit to the data by generating the response. And those are a series of recursive reduction steps by tweaking the model, going through again, going through again. Almost identically, the machine learning recursion estimates certain types of geobodies. That's really the name of the game. I haven't introduced geobodies yet, but the fundamental goal is just like a horizon auto picker, but now we are using machine learning for geobody auto picker, and we're looking for geobodies that share common seismic reflection character. That's data adaptation, and this is error correction without data adaptation. There's a concept here of feature space and latent space. If you're in psych or economics, you'd be much more familiar with latent spaces, because latent spaces are sort of for the soft attribute problems that you're trying to tackle. Feature space for us would be our seismic attributes. Our seismic attributes, every sample in the 3D survey with its attributes is a sample in feature space. Pardon me, it's a vector. Latent space, if you were in psych or economics, we have latent variables which are not observed directly, they are inferred. For example, you've analyzed a patient, and you've concluded that this patient is normal, and the next patient comes in, and this one is a psychopath, that sort of thing. Those are all inferred after judgment evaluations. So there's only one true feature for us, and that's the amplitude. The rest are derived from the base survey. So you would say, really, the only true thing that we've got in a 3D survey is the amplitude. Everything else is based upon the amplitude. So it's a latent variable which sits in a latent space. So where up here we would think, well, you know, seismic sample, it's the good stuff, and we have nothing to do with psychology. Well, hello, yes, we really do. We have samples that are derived from other samples, and that puts us in an inferential situation in a latent space. We have latent vectors then, which reside in latent space, and we have hidden variables, which are possibly related to variables that are hidden there, and maybe they're not. So there's hypothetical variables, which are abstract variables, and there are possible relationships there that are important. All this ties together so that latent space dimensions are the same thing as feature space dimensions, but how you tackle the problem. If you have hard attributes, that's pretty straightforward. Latent requires human intervention often to complete the productive analysis. So in terms of dealing with the psych, we're going to have something like this. There are, believe it or not, if you crack open Wikipedia, you'll find out there really are 5 properties of your personality. Psychologists have kind of agreed upon this: openness to experience, conscientiousness, extrovertism, agreeableness, and neuroticism. Okay, those are your 5 properties. So to describe you as a 5-dimensional space, if you will. Hey, we got 5 instantaneous attributes. We got a lot more than that. We've got maybe, I don't know, 20, 25 instantaneous attributes. But you see, the point here is that in the case of personality trait, that's you. That's me. That's your kid sister and your kid brother, okay? And you're a single sample, and your properties are personality traits, for example. We're dealing with amplitude, and you can say, well, that's the only one that's any good. Nah, there's others in there, and the selection of the attribute list is specific for a problem that we're trying to address. So here we got, this is important, classification helps us focus the mind, but it isn't the answer. It's not the result. You just can't look at the results of a machine learning classification and say, I'm done. There's the classification. It's time to move on. No. Successful classification has to be followed by successful predictions. And they are the results of successful classification, and then refinement, adjustment, and further analysis. That's what makes this thing important. That's why I put a little star on this page right here. The value of machine learning classification, very, very helpful, but it's not the answer. It's not going to replace you. It involves your judgment. You're dealing with not a hard attribute space. You're dealing with a soft attribute space, and your opinions and the way you conduct the analysis are important. Now, there's all sorts of ways of classifying different algorithms. For example, accuracy is one measurement, because you're going to have not only your guesstimate of classification, but you also know what the real answer is. So you have false positives and of course, false negatives as well. So there's really 4 choices here: true positives, true negatives, false positives, and false negatives. And these are some algorithms here. For this data set right here, these are the results. And accuracy is one of the measurements of the success, and it's 0.9 for this one, 0.8 for this one, and 0.7 for that one. And for a different set of data, you're going to get different accuracy measurements, and for a different set of data again. So what's the bottom line in all this this business about multiple machine learnings? Which is the best? Well, guess what? From the shown in the table, can we conclude that AdaBoost, if you're reading fast, or random forest was the best algorithm? The answer is no. That's for these 3 sets of data. The answer can be numerically defined. But does that really deal with the problem? The results are nice, but they suffer 2 very, very important limitations. Limitation number 1, will this algorithm work best on my data or your data or tomorrow's data? And then what about this no free lunch theorem that was lurking back there that I introduced a little bit ago? Is there a best algorithm? Consider the no free lunch theorem. Very important. And the no free lunch theorem, being a little more specific about what it really is, it states that a certain problem optimization to get to the answer fast enough, it averages out over similar input data. The key to success is to clearly understand your problem that you started with, collect the right data, and select an algorithm that handles the job. That's what's the important thing about this. If you are a geo nerd, and if you're a geo nerd, welcome to this session. You're more than welcome, and I love to have a geo nerd discussion. But let's take a look at some geo nerd buzzwords. We have some supervised and deep learning algorithms like CNN, random forests, PNNs, GANs, and support vectors. Support vector machines. This first column is supervised machine learning. Unsupervised machine learning and mixed machine learning. We've got k-means, k-nearest neighbor. Of course, SOM is a popular one. DBScan is another. There are various autoencoders and neural networks. So you might hear a geo nerd say, oh, well, we've been using CNNs for some time now, and they work fine for us. ... Just leave that at the end. Or you have somebody else that says, whoa, we use CNNs and GANs, and we found they were inadequate for us. I can't talk about our secret algorithm, but it's much better than anything on the market. Those are buzzwords from our GeoNerd crowds, and just urge you to be careful. Put all of those sort of quests for the golden arrow, treat them with a little bit of a gingerly skepticism. All right, we're going to take a look at supervised and unsupervised machine learning. And in this case, here's a 3D survey, just our amplitude display, and then here it is in SOM. And here it is by using SOM and deep learning for faults. And we're looking at just the back faces and a time slice across here. So this is what we started with, and we used unsupervised machine learning to classify the data with a set of, well, we had two very important things to decide to do the SOM. We had to decide which attributes are going to be used. That's key decision number one. And key decision number two is, well, what was the dimensionality of our self-organizing map here? 8 by 8, well, hello, did you try 5 by 5? Did you try 20 by 6? You know, to what extent? Those are the two fundamental questions that need to be decided. This is the new ground of machine learning seismic interpretation. But now you're not deciding about what should be my window length for my auto picker for my horizons and trying to find some flooding surfaces. Yeah, it's that, but now it's a whole new level of using machine learning tools. And this was unsupervised, and then this one for deep learning is deep learning for estimating the location of faults. And you can see down here across the bottom, the two are working hand in hand. Look at this. The fault work that was done here has nothing to do with the SOM result, and yet they're tying together nicely. Okay, so now not only are we finding where are the fault blocks, but we're also then starting to sort out what are the characteristics of the data in this fault block versus this one over here. What about the blue stuff? What is that? You see how this stuff sort of builds on itself? It's really good, a lot of fun. And challenging, yes, but also our ability to make better predictions, which is our bottom line, is more important. Here's an example from my friend Deborah Sacre, East Texas. And look, how would you, if you just looked at this, would you realize that there is an incised valley here from the seismic? Sure. This is basically the awesome chalk, by the way, that's been auto-picked across here. So how can one tell where are the productive sands in this incised valley? Yeah, that's kind of important. Well, here's the data after unsupervised machine learning. And here's a blow up in the vicinity of the well. And this is not done just as a magical step here, but this is the new style seismic interpretation. And yes, this is the best, most productive results of what the prediction is away from the well. And this is a particular well right here that was drilled. It's what made 1.8 Bs and 172. Another one from Oklahoma, machine learning SOM. This is a SOM on this one. And then notice something pretty interesting here. Probably not all that obvious, but look at the repeated section. Based upon this repeated section, inferred that there was a thrust fault coming through here, that this is the thrust fault. I defy you. I bet you a cup of coffee and 5 donuts. Let's make it half a dozen, 6. I defy you to look at the amplitude data and infer with geologically identifiable features like a low angle thrust fault. If you want to take me up on that, I'll get my cup of coffee and we'll start picking out donuts. All right. So if we can sort of put this thing together, our goal then is for seismic interpretation. We start off with a survey. We generated MOLDA attributes. We ran a SOM, for example, classified the survey, and then we've got a whole suite of bunch of geobodies. Not everything is a geobody of geologic significance, But those things that are important are geobodies that we can do an interpretation on. There's going to be other stuff in there like acquisition footprints. It's coherent energy. It's going to show up as a natural cluster in attribute space. Yeah, well, those are just other machine pick geobodies that we dispense with. There's no good geology in them. The point here is that we are now working with multi-attribute surveys. We are now working down on a sample level, and yeah, it's not perfect. This is a statistical process, but there is some important values of using attributes that takes us closer to the geology. Our goal is not to look at these little, what Deborah calls chiclets here, which are the individual samples. Our goal is to infer continuous regions of the same thing, classified. This is colored up like a cyan, I guess that would be. And so that's one geobody. There's another one over here. This is an example, again, from Deborah of these are some wells that were drilled, and these are the results down here. These are the geobodies that resulted. And you can now correlate that what was encountered on these two boreholes is separate from this one here. This would be a valid prediction that you would make. It's not magic. It's based upon you being a fundamental part of this process. Making geologic geobodies and using machine learning was done on the Stratton field, and then classify them as bars, discs, blobs, truncations. This was done several years ago. So here's where we're going on this. We would say that with supervised machine learning, you would say, well, look, I'm going to evaluate how well this black box classification matches my answers. That's what supervised machine learning is all about. I pick labels for my training data. In unsupervised machine learning, well, I got black boxes again. I got some classifications out here, but I have to look at everything, and some of it's going to make sense and some of it's not. You see how close these two are? And literally, they work hand in hand with each other. So I urge you to consider the no free lunch theorem. Geoscientists should play an integral part in all stages of the data analysis. This is the new seismic interpretation. Key to making better predictions, which is our goal, is making better reasoned decisions along analysis flows. So the algorithms that work best for everything does not necessarily mean it works best for your problem, because if it works good for the average, you're going to have some pretty good results and you're going to have some pretty bad results. Algorithms must be chosen to really focus on what is the problem. Problem comes first, not the algorithm. That's why this is a cup page. And I'm going to move this over here on the right, on the left, because I want to add something on the right. And that is the following. Tell your boss that because of the no free lunch theorem, your presence in the company is necessary. And the boss cannot replace you with machine learning because of the no lunch theorem. That's why this is important. All right, let's take a look at the fishing analogy very quickly here. We're running a little short on time. Take a look at fishermen. Fishermen and geoscientists, believe it or not, are in the same business. Don't believe me? Well, hear me out, please. Fishermen, what do? They sit for hours and they discuss and discuss and cuss and discuss and then cuss some more and discuss some more about who's got the better seat, the guy in front or the gal in the rear or vice versa, whatever. They discuss who's got the better seat. They discuss where to fish. Should you fish along the shoreline? Should you be out in the middle somewhere? And they argue about the bait. Should we be using artificial bait or should we be using live bait? They discuss what's the best time of day to go fishing. Now, later, well, what about the moon phases? What about this? What about something else? And they ask who brought the beer? But fundamentally, they all want to catch the big fish, don't they? That's the optimization function. All these questions that you saw before there are part of the optimization problem. They want to maximize the size of the fish, and they want to minimize the time between fish strikes. They want to get the big fish that are all in a school. So it's a maximization and minimization. And then they might even wonder, gosh, maybe this is a crappy lake. Maybe I need to go to another lake and go through this whole analysis again. They even would discuss how to retrieve the lures, fast, slow, or should you jig it? And they recognize fundamentally the way to catch fish is to keep the lure in the water. That's the fundamental law. In the oil and gas business, it's who's going out and who's trying to replenish those reserves. Now you're starting to get the message here. There's a lot of similarity. Geoscientists and fishermen are both in the business of prediction. And it's the boss's job to decide where to drill. It's not us. We just lay out the analysis, our logical sequence of how we arrived at our predictions. And our job is to make those predictions, make recommendations on where to drill, but the boss writes the check. They recognize that the way to catch fish is to keep the lure in the water. Our job is to continually improve our predictions for the help of the company. So there's a case here of machine learning interpretation. Unfortunately, we're not going to have a whole lot of time to go through it. It's in the EA first break, July of this year. Manucci Cherry Pham, Helleman, Rocky Roden. And it's a multidisciplinary approach of the Wisting case study in Barents Sea. And it's particularly valuable because it is an example of using machine learning first for classification, but then following it up with a regression. And here's the bottom line: interpretation. It's only the first step in prediction. Okay, we go through our process of seismic interpretation. It's only the first step. We haven't completed things there. Predictions are not found in this presentation, but to keep the company healthy, it's the predictions that help the company stay healthy. And that's why this is again a gold cup idea. So here's the Wisting. We're going to do this in two steps. First step is we're just going to look at the data, and then we're going to look at the analysis. So here's the first part. The Wisting case study was an interesting validation of machine learning. Barents Sea, this is Norway, by the way, and we're way north up here. There's two fields. One is the Wisting field and the Hansen field up in the Bering Sea. Geologically, these fields are in the Stowe formation of the I believe that's pronounced Grunen subgroup, okay, which is Triassic and then into the Jurassic. And the Stowe was classified by the company that presented, the people in the company that presented this paper, as a flow group 1, and it's a shore facies and estuary sandstones. There was a thought that perhaps there was nonconformity on top of a second flow group, and then there's a third and the fourth flow group. The second one, RG2, is what we'll be looking at some results here quickly. It's a multi-story, multi-level fluvial channels with mud class and sporadic abandonment and fills. Get a little complicated, and because we're dealing with muds class, not necessarily mudstones, but the acoustic impedance contrasts are very subtle. And trying to get anything sorted out it's a lot of fun. This is the reservoir analysis steps that were used. There was some SOM, and then there was a second SOM of reorganization and tying everything together with the reservoir properties from these 8 wells that were used. The key to successful reservoir was in this area was porosity and clay volume. The attributes that were used were envelope, acoustic impedance, and attenuation. And there's a very interesting discussion of how they arrived at these 3 attributes as the critical ones to get where they wanted to go. I urge you to read the paper. Also, making a decision. This was an 8x8 neural network, And they did a careful analysis of using other neuron topology to see which is the best one to use. But anyway, let's take a look at how they got this thing to work. Well, we know that from our seismic data, either depth or time, we have a SOM winning neuron, okay, which is a vector at a particular depth. And then we have some set of rock properties at that depth. So the link between the winning neurons and the rock properties is the well depth. Critical, critical, critical. You better be dead on your time depth curve. Dead on. I mean it. Right down to a sample level. You need to be dead on. You don't want to be sliding that thing up or down because we're dealing with multi-attribute seismic samples. So we have an attribute selection list. We also have borehole seismic samples. We can extract the seismic data along the borehole, and we also have our stratigraphic features, our reservoir features. So we have 3 different groups here that we have to tie together, and this is the checklist of picking out the right SOM training and then going through this checklist to make this connection so that you can link the classification to rock properties. One winning neuron is linked with one set of rock properties as one statistical sample. A set of samples are tested for correlations between the winning neurons and the rock properties. Critical, critical, very important. Geobodies are constructed from the winning neurons with the rock properties. These are the properties, and we're not going to consider the problem of physical models here. I'm skipping past this, excuse me. But the bottom line is that when we have a series of factors that are important, even if we don't have a physical model, as you would find with those rock properties, you can still make relationships. We're using science to discover that. I'm going to close here with a couple of slides here. This is a 3D survey P cable was used in the Barents Sea up here. This is the seismic. They ran a conventional acoustic impedance analysis, and here's tying the acoustic impedance with the rock properties, total porosity, and V clay. And the red here is, as opposed to the sort of blue-green, the acoustic impedance estimate of V clay, and red using SOM, and over here on the other one as well. These are for 2 wells. Well, it's all in the paper. They concluded that using the SOM results were superior than using just the acoustic impedance results. They compared the results not only in section, but they compared it in time slice, and made some geologic predictions that were better than they would have had using acoustic impedance. Here's the second rock property that was important, of course, was total porosity, I mentioned. And they used co-creating, interestingly enough, used the 3D SOM results and the co-creating estimate of the trends to estimate the total porosity. So that's it. I would just like to conclude by saying that I urge you to be careful. A lot of machine learning is based on averages, and the oil and gas industry, we're not interested in averages. We're interested in anomalies, something entirely different. Supervised machine learning, if you don't have the right training, examples of everything, don't expect machine learning to find it for you. It's not a black box. In unsupervised machine learning, the anomalies are found either in clusters or they're found in low statistical probabilities. Use averages where appropriate and look for outliers where appropriate. And that's why this is very important. So the checklists are the following. What's the problem? Get the right data. Select the right training data for both supervised and unsupervised. Select the right algorithm. Don't cheat the algorithm out of a good answer. Let it run to completion and then study the results, because you're critical for coming up with the right answer. You're an integral part of making better predictions. With that, I'm done. Sorry to be 7 minutes over. I think Laura will hook us up to a chat room where I look forward to discussing what's going on. Go ahead, Laura.
It's just the chat here in the meeting. You can feel free to submit your questions there. Alternatively, if you're watching on the YouTube channel, you can just go to the comments and put your questions in there and we'll get them. So I'm going to go ahead and open up the floor now. The YouTube is on a little bit of a time delay. They're about 30 seconds behind the Teams meeting, so we'll give people a couple more minutes.
Well, here's another possibility. If you're getting hungry or if you got other things that you need to take care of, send your questions and we'll be glad to respond in writing. That's another opportunity.
Indeed, indeed. Looks
Of course,
like
if you want an answer, you're going to have to give us an email address.
That is true. That's true. Looks like we have another one coming through here. Just a moment. Tom, if you go to the chat icon, you've got a lot of people commenting on your presentation. They say it's good stuff.
Where's chat icon? I gotta find
Up in the top bar, it's the second icon, the little one that looks like a little like conversation box. You've got the people and then the little, yeah, there you go.
Show conversation.
There you go, right there.
All right, great.
Yeah.
All right, let's go to it.
Okay, quick question. Is Geophysical Insights participating in the Schlumberger hybrid cloud?
We're evaluating it, and we don't have any deal signed with them. The Gaia is a very interesting concept. We're a little bit different, though. If you're going to write a boutique machine learning algorithm and plug it into Gaia, the beauty of Gaia is the worldwide access to data. It's awesome. So if you have a numerical algorithm, a boutique algorithm, that seems to me like it would be a great place to hang it. However, we're focusing on something a little bit different, a workbench. It's the Paradise workbench, if you will, of not just one magic answer, but the whole set of tools that you would use to interact. For example, combining SOM and deep learning for faults as an example of today. And we'll continue to build on our workbench as we grow with additional tools, with the focus on using machine learning as a tools, just like you would have a screwdriver and you have a hammer and you have a wrench and that sort of stuff. How you put things together, that's how you make better predictions.
Perfect. All right. I think with that, we can go ahead and wrap it up.
Thank you, everyone. Appreciate it.
Thank you. Have a nice afternoon. You guys, our next presentation will start at 1 o'clock, so we invite you to come back and join us for that. Bye-bye.
Thank you, guys. Yeah, bye-bye. had to go back and restart. Now I'm in. I don't know. I thought I was sitting in the meeting all the time.
Well, I'm glad to have you here now. Do you have your presentation ready to go so that you can share your screen?
Well, I think it's going to be better if we do what we did yesterday and you advance for me. Can you do that?
I can. You want to go ahead and send it to me?
Okay. I need to send it to you again, do I?
Oh, it's the same one, huh?
Yes, ma'am.
Okay, that's fine. I can go ahead and pull it up. Give me just 1 second.
That's it.
Okay. And with that, we can go ahead and get started, ladies and gentlemen, and those of you joining us on Teams and YouTube. We are going to be talking today. Bob Hardage is going to be talking about investigating the internal fabric of VSP data with attribute analysis and unsupervised machine learning. So if you will please type whatever questions you have into the chat, either here in Teams or in the comments in the YouTube live stream, and Bob can answer those verbally at the end of the presentation. Thanks so much, and without further ado, here you go, Bob.
Thank you, Laura, and sorry for the late start, people. I thought I was in the meeting, but turned out I wasn't, so I had to go back and restart. Laura, advance one here. We're going to try to move a little fast here, and I'll be talking back and forth to Laura because I'm having trouble launching from my end. I'm up in the state of Ohio, basically on the Michigan-Ohio border, and maybe things aren't working too well here. But let me tell you what I'm up to here. I have a very fundamental research focus that is going to benefit, I think, our industry and also geophysical insights in the expanding the market to whom they can offer their unsupervised machine learning software. And that purpose is to get our industry to raise shear wave reflection seismology up to the same use and prominence as P-wave reflection seismology is and has been now for several decades. And there's really a kind of a simple answer why shear wave reflection seismology has not been widely accepted in our industry. And it's a problem at the source end. And so what I have on the screen right now is a little cartoon that kind of summarizes how our industry has practiced the acquisition of seismic shear waves in the past. And you can see that in the first row across that PowerPoint, I have a clock time. And I'm trying to show that in order to generate shear waves, 3 different sources had to come to a source station at 3 different clock times. And the second line of the diagram shows you the displacement vector that each of those sources applied to the Earth at that source station, a vertical one, Z, then a radial horizontal one, X, and a transverse horizontal displacement, Y. And the bottom line then shows the various wave modes that were captured by each of those source inputs. And so to get real complete shear wave data, you had to function this way. And right there lies the problem. That's very expensive to use 3 sources rather than 1 source as P-wave data are acquired. And the only effective horizontal displacement sources are vibrators. That's why I drew a truck there, because that's really about the only effective horizontal displacement source our industry's come up with. And you cannot pick up the telephone right now and find a horizontal vibrator to use. And even if you could, then there are many areas across the Earth's surface where you cannot use it. Swamps, marshes, dense timber, very rough mountainous terrains and so forth. But in all of those surface environments, we can use some kind of a P-wave source, either a vertical vibrator or buried explosives. And so what a small group of us researchers have established right now is that, advance the slide right now, if you would, Laura, please. That what we show here is a simple vertical vibrator, and that one vibrator makes only one visit at clock time T1, and there is a way to get a direct downgoing shear wave from that vibrator, and also from a buried explosive source, that works just as well for imaging deep geology as does the direct P wave generated by these sources. So Laura, advance one more time. Therefore, why are we talking about VSP data? Well, probably the biggest technical problem that I am encountering on trying to get our industry to understand that you can use P waves for S wave illumination is that there's been a study done way back in the 1950s that calculated the P wave and shear wave illumination patterns that are generated by a vertical vibrator. And that study showed that, yes, there was a lot of shear wave energy produced by a vertical vibrator. In fact, more shear wave energy than P energy, but none of that shear wave energy traveled away, let's say, from the base plate of a vertical vibrator in a vertical or near vertical direction. In fact, it would be a cone like plus minus 30 degrees away from vertical, that there simply was no shear illumination. And if that isn't true, then yes, you cannot use a vertical vibrator for shear wave reflection seismology. Your downgoing illuminating wave field has to leave the source station in a vertical direction and have a rich amount of energy in small takeoff angles from true vertical. Therefore, we look now, or I look now at VSP data, because if you want to see what goes down from a source, then VSP data define that in a very rigorous way. And if you want to know if the energy is traveling vertically, then look at a zero offset VSP. And so that's what I have drawn here is a zero offset VSP. The receiver stations, the black dots, are going up close to the Earth's surface, and BP, that's the base plate, say a vertical vibrator, and I'm showing an area around each of those base plates that have their physical size of that gray shaded area depends on whether the velocity in the layers at and near the surface have a slow velocity or fast velocity, because that shaded area is what we call the near field zone, and that is that zone around an illuminating energy source that extends out for a distance of one wavelength away from the point of energy generation. And the first wavelength of the propagating wave field is created in that near field zone. And therefore, it is very difficult to look inside that near field zone, because how do you look at seismic wave fields when not even one full wavelength of the data are generated? And that is the technical problem that makes some zero offset VSPs difficult to for you to backtrack a downgoing P wave, S wave back up to the surface and prove with great confidence that yes, it was generated directly at the surface where the base plate is. So I've looked at a lot of VSPs in slow velocity media where it's very easy to show that. The problem is when you get into a fast velocity medium and those shallow geophones are inside that near field zone, then there's really some serious problems that pop up, and that's what I'm going to show you here, and then expand that investigation to show you how unsupervised machine learning is just revealing things in VSP data that I have never been able to see before. And probably some of you know that I wrote the first book in the English language on VSP back in 1982. So I've been in this VSP game a long time. And for me to say that, hey, I'm finally finding a way to investigate those data that's telling me things I have never seen or realized before, I think it's worth listening to me. And that thing that I'm referring to that's doing that is unsupervised machine learning, which is a capability that's offered by the Paradise software provided by Geophysical Insight. So Laura, advance me one more time here, and I'm going to move a little bit quicker than I did yesterday to try to get through all this material. So there's a definition of the near field zone. You know, it just says in words what I have spoken verbally here. And advance again, Laura, if you would. That this diagram here shows you the actual zero offset VSP that we'll be looking at. The rocks in the near surface or fast velocity. I have them labeled there in the lower right. If you can see that, VP's up to 10,000 feet per second in the surface layer. So the wavelengths are long, and the actual depths of the geophones are shown on the left by the numbered circles, 1, 2, 3, 4. It's 50 feet between adjacent VSP receivers. And certainly the first two and maybe the first three of those receivers are inside that near field zone. So keep that in mind. This may be the first time you looked at VSP data, that is, in trying to look inside what we call the near field zone. Advance me again, Laura. Okay, and we're going to look at a lot, or I looked at a lot of instantaneous attributes, and I'm going to go through these kind of fast because there gets to be a little bit of redundancy. I realize now that I've made this presentation once, but the two instantaneous attributes that were really helpful in looking inside the near field zone are those two in the rightmost column there that have the double asterisk, that being the instantaneous phase and the relative acoustic impedance. And you'll see evidence of that in what I'll be showing you pretty soon. So advance again, Laura. Okay, these are the actual data. And it's divided into the panels like we typically do with VSP data. Vertical geophone responses on the left, radial horizontal geophone responses in the center, transverse horizontal geophone responses on the far right. And first thing I probably need to point out is that if you look up here in the extreme upper left corner, you can see that here on the vertical geophones, I'm pointing at that. I don't know if you can see my pointer moving on your screen or not. I hope so. But that shows that these there's wavelets going all the way up to the shallowest geophone, which would be inside the near field zone. So you might ask the question, hey, what's all this nonsense about not being able to look inside that near field zone? Well, the new gain that's been applied to those data is just tremendously large. And what you will see is that when you try to calculate instantaneous attributes, you cannot get any instantaneous attribute to go inside that near field zone. It's just like it's a haunted house here at Halloween time that I'm not going to go in there, boss, you know. And so that's telling you that there's things going on with the data inside that near field zone that are different than the data are outside of that zone. I'll very quickly get to some instantaneous attribute displays that will convince you what I'm saying here. But we're going to look at these data now a little bit more closely, and specifically, we're going to expand the data up in that upper left corner and concentrate just on these upgoing events that are originating somewhere at the base plate. So Laura, advance again, please. So here is a zoom view of just the vertical geophone data. And now for the first time, look at the responses. That's the geophone receiver stations going from left to right horizontally there. And look at where receiver stations 1 and 2 are, and where's the data? You know, there's something making some colors in there, but basically that's telling you there's no data in there, or the data are tremendously changed for whatever reason. And even from about receiver station 2 on down to receiver station 6, the data are faded, but it's still, very believable data in that zone. So Laura, advance again, and now then we're going to be looking at some of the attributes. I said that instantaneous phase was very helpful on backtracking things into the near field zone. And here you can see these phase lines, those yellow lines, that you can follow a deep yellow line all the way up to receiver station 1. which is definitely inside the near field zone, and the phase lines do not seem to have obvious breaks as they transition from near field zone to far field zone. So that's encouraging that, maybe some attributes can kind of probe into that near field zone in some way. Laura, advance me again, and we may move pretty quickly here if I know where I am. All right, now then, we're simply going to I want to flash this back again so you can kind of see what data I'm looking at. We're going to now look at these radial horizontal geophone data in the center panel. And now then, you can see a downgoing P sloping down to the right, but there then are these events here that are also sloping down to the right at later times that are traveling with slower velocities, and those are shear waves. Now, if you go to the first one of those, and it's labeled converted S in the white oval circle, you can follow that back upward to shallower receiver stations and see where it intersects the P wave, at a depth of about, receiver station, I forgot, 12 or so. And so that's a converted shear wave where the downgoing P at a rather sizable reflection contrast, impedance contrast, converted some of its downgoing energy into downgoing shear and created that shear wave. But then there are other shear waves at later time, and so there's a white oval on the extreme right of that radial geophone pattern that's labeled direct S. And if you try to track it back up, you can kind of see that its slope is going to take you almost directly up to the surface, but you cannot, with great confidence, track that event through the shallowest part of these data. It's just too jumbled and complicated there. So Laura, advance again. And here is a zoom view of the radial horizontal geophone data. And we get the same effect we did with VSP data. If you look at the response of certainly geophones 1 and 2, it's just saying, boy, I'm losing almost all my data character and these geophones. And that's where certainly the near field zone is. And then about receiver station 3, well, you kind of see that the data begin to convert into the black-red peaks troughs that we are used to seeing in our data, and you get a little bit more comfortable that, hey, it looks like kind of ordinary data that we're used to working with begins to appear and become usable about receiver station 3, which, as I drew the diagram some slides back, was where I thought the boundary of the near field zone probably extended to. Let's see, Laura, let's advance. I think we're going to advance two slides. Yeah, go on past that one. Oh, right there. Now, here is one of the attributes that was quite definitive on trying to backtrack these downgoing PNS data to their points of origin. And if you can read the label up there, that is the relative acoustic impedance that you can derive probably from anybody's instantaneous attribute package. Certainly you can from the Paradise package that Geophysical Insights has. And you can see I've added some black dash lines there that kind of help you visually see the trend of energy movement that I'm trying to backtrack. So you can see where the direct P is up there. That's a fast traveling velocity. Then these dash lines that have a greater slope to them, that's a slower traveling package of energy, and that's the shear wave. And if you look at the one that's labeled direct S, well, you will see that those dash lines, you can extend them with great confidence up to receiver station 5, and then you sort of get a little jumble there, and you have to decide, do I follow the lower green or cut across a red and go to that upper green? But basically, it's going to terminate somewhere in the vicinity of 100 milliseconds. Now, let me hasten to say that the instantaneous frequency instantaneous phase attribute, arrived here at receiver station 1 at roughly 50 milliseconds, okay? And the VSP receiver well was 195 feet away from the source station. That was labeled on the diagram. Probably there's just too much clutter on that diagram for you to maybe catch that detail. So the distance from the base plate to the receivers 1 and 2 is, in round numbers, it's 200 feet. And so if the P-wave velocity got there at 50 milliseconds, well, it's and we have pretty competent high velocity material there in the near surface, which is obvious, I think. Then the VPVS velocity ratio of about 2 would be reasonable to assume. And so if you make that assumption, then that says shear wave arrival at that station. If the P wave arrival is 50 milliseconds, the shear wave arrival should be about 100 milliseconds. And you can see that's where that black dash line is trying to lead you, okay? Advance one more time, Laura. Okay, now we're going to look at the transverse horizontal geophone. I'm not going to talk too much about the wiggle trace display we have on the screen. You've seen it several times now. Advance again, Laura. And here is the phase, same as before. You can backtrack them. Certainly, the P wave, you can backtrack it up to the surface. And then there's slower traveling phase alignments that have to be shear waves. And it's a little difficult to track it through some of the mess around the receiver stations 11 to 15. There's just a lot of upgoing P wave reflections cutting across the downgoing shears at that point. It complicates phase relationships. But you can kind of see that there is a phase line that is, again, bringing you into maybe just a little bit below the 100 millisecond timing line. Advance again, Laura, and we're going to look now at that same attribute again, the relative acoustic impedance. And here it is, and again, now you can see where the trends for the direct P and for the direct S are drawn, and that trend for the direct S, it again brings you to receiver station 1 at a little bit past 100 milliseconds. And so again, here for this most difficult type of zero offset VSP data that you can find to backtrack downgoing events to their point of origin, that being a zero offset VSP that is acquired where there are high velocity materials and layering immediately at the surface. We have been successful here on showing, okay, even in that most challenging type of backtracking environment that you can have for zero offset VSP, we can still backtrack the downgoing P and S to show that they were both generated at the surface source station simultaneously. All right. Now let's advance again, Laura, and we're going to transition now into some machine learning concepts. And the first thing I want to do is calculate the principal components of the P and the S data. And advance, Laura, while I continue to talk, that the principal components that advance past that again also, Laura. Okay, we're going to look at principal components of both of all three geophones. That's the reason I flashed the wiggle trace geophone data there again, that I asked her to just take off the screen. And we start, of course, with the vertical geophone data here. So the PCA, that means the principal component analysis. So what is a principal component analysis? I'll give you a very quick version of that. The dimension of the attribute space that we're dealing with here is relatively large. I showed you just very, very quickly back at the start the list of instantaneous attributes that were calculated, and there were 15 of those. And there's actually 16 attributes because the input data from which all those 15 attributes were calculated, those input data are also an attribute, and that's 16. So the attribute space that we are dealing with is a 16-dimensional space. And what principal components try to do is two things. Number one, they say no one can really work in a high-dimensional data space. You can't see what's going on. Our human mind can't go beyond 3 dimensions in visualizing things. So how can we reduce the number of dimensions down to something that is manageable? And the second thing the principal components do, it allows you to actually throw some of the attributes, dismiss them as being of any significant value in whatever analysis you want to do. Now, let me show you how those two things work here with these data. Now, we're looking at principal components that were determined for the vertical geophone data that now you've seen displayed several times. And the height of those black spikes that you see there, those are indications of the amount of attribute information that's embedded in this principal component. If you have a 16D data attribute space, then you will also have to have 16 principal components. And so the components are numbered down on the bottom, 1, 2, 3, 4, and principal component 1, that is the first one that's created. And so when it starts looking at the data in every attribute space, it is free to go across that data space in any direction it wants to go. And so its mathematical requirement is find the largest dimension of that data space and go that direction, and do the same in the second attribute space, the third attribute space, and so on and so on. And so principal component 1 gobbles up a huge amount of information. All right, now then you're going to make principal component 2. And you can see on this diagram that its amplitude is smaller. But the reason that it is smaller is that the mathematical requirement of making principal components is number 2 principal component. You also can look through all 16 dimensions of this data space and find the largest dimension in each one of those spaces and this is the important requirement, you can only do that in a direction that is normal to the direction that any previous principal component went through that data space. And so principal component 2, it still can look at a big variation in the data when its requirement is that every direction it looks has to be normal to the way that principal component 1 went through those data. And then you come to principal component 3, and it's allowed the same freedom. You can go through every dimension that is available to you as long as the direction you go is perpendicular to the direction that both principal component 1 and principal component 2 went through those data. And so you can see that as you go to higher dimension principal components, this mathematical constraint that they have to probe the attribute space in directions that are perpendicular to the directions that all preceding principal components went through that data space, they just, that's why you see the amplitudes just decrease. And so what we're seeing here, that those first 3 principal components here, they actually provide you 50% of the total information in the attribute space. And so in my decision, that's the only 3 I'm going to work with. Others may say that's not enough. I want to at least get 60% of the information or 70%. It's a personal decision. But we're going to go forward here saying we're just going to work with those 3. We're going to get 50% of the total information, and that's going to be enough for us to make viable decisions about what's the fabric of this VSP data. Now you'll see the arrows that peel off of the top of each of those eigenvalue spikes and point over to the right to a box that lists specific attributes. And those are telling you what attributes contribute to the information in that principal component. And you can see the labeling there is getting a little fuzzy, I can see, and it may be difficult to read. These PowerPoints should be on the Geophysical Insights website. You can download it and look at them, at your leisure. But you can see that it's only taking 3 attributes to give 75 and 90% of the information that's embedded in each of those eigenvalues. So now then, hopefully this explanation has helped you see how principal component number 1 reduces the number of principal components that you need to consider in order to get the total information in a database, and it allows you to reduce the dimensions. The dimensions are what's in those boxes on the right side. That's the actual dimensions of the data space. So Laura, advance again. And this is the principal component analysis for the radial geophone, and you'll see things are essentially the same. The first 3 eigenvalues are they're the big bruisers that capture. This one didn't quite get half of it; it got 47% of it. And then again, it only took in the boxes on the right. It only taken 3 attributes to contribute almost all the information that's in those 3 principal components. And advance again, Laura. And now here's the principal component analysis for the transverse geophone. Same story. And in fact, if I wasn't going so fast and we could talk and ponder a little bit slower, you'd see that the numbers is about percents of things, and the attributes that are listed in those boxes, they are just identical essentially for the horizontal and transverse horizontal data. So we're going to kind of now and then look at these conclusions, I think, in some tables, if my memory's right. Advance again, Laura. Yes. So now then, the left column here is showing the 3 databases that we have analyzed with principal component analysis: the vertical geophone data, radial geophone data, transverse geophone data. And we decided, okay, we're only going to use the first 3 eigenvectors, and so that's the column of information that extends to the right. And then I list under each of those eigenvectors the specific attributes that contribute their information, and in brackets the percent of the information that they do contribute. And let's look down these. First of all, let's look down the vertically. What composes a eigenvector 1 for each of the 3 geophones? And if you look eigenvector 1, look vertically down that first column, all 3 attributes are identical: instantaneous frequency, thin bed, acceleration of phase. And that's telling you that eigenvector 1 is exactly the same for vertical geophone data, radial geophone data, transverse geophone data. And people, that's what kind of set me back on my heels, because I was thinking, hey, no way, because P waves, and shear waves, they probe rocks in orthogonal directions. And this is telling me that they're probing a rock, say vertically, and then one probing it horizontally, and they're getting the same attribute information, irrespective of what direction that displacement vector for each of those wave fields is oriented. That's what this says. But my brain wasn't ready for that, so I've got to kind of reset some things in my brain. Now, if you continue over to eigenvectors 2 and 3, you see the same thing. Look at eigenvector 2, that column, that first group of 3 at the top. All right. Now you go down to radial geophone. Those 3 there are not the same. But look over at eigenvector 3 in the second row, and there they are. And if you remember, eigenvector 2 and 3 had almost exactly the same amplitudes in the PC analysis graphs that we just passed through. And so if you have time to look at this later, why it'll show you that the attributes in eigenvectors 2 and 3, they are exactly the same too. There's going to be two of them that switch it, which eigenvector they want to belong to, but both eigenvectors having essentially the same amplitude. It doesn't matter which of the two, a group of these attributes decide to be in. And so the bottom line here is that the PCA analysis is saying, hey, Bob, these particular zero offset VSP data, they've got the same attribute fabric in the vertical geophone response as they have in both radial and transverse horizontal geophone responses. That's news to me. All right, advance again, Laura. Okay, now we're going to go kind of quickly through this concept of self-organized maps. And this is where you really see the power of unsupervised machine learning. And so what the concept of self-organizing maps are, I'll give you my kind of layman's description of this, which is not going to be maybe as rigorous a theory as it should be, but nonetheless, what self-organizing maps does is that it creates some entities that we refer to as neurons, and it lets those neurons probe through all of the database that you're wanting to examine, and those neurons search for where there are certain combinations of attributes that have certain percentage contributions to themselves, and a neuron likes to build a cluster of image points where he or she, whatever you would call this neuron, where he finds this condition of here's the attribute combination I'm searching for, and these attributes are ranked in the percentage of importance that I want them to be. Those are my people. I hope that made a little sense. It's the graphics I think are going to be coming up now will maybe help you a bit on seeing what I'm trying to explain. Laura, advance again. All right. When you use these neurons, you have to create a neuron family, and the family that I created are the 25 objects shown in the red grid on the left there. Each one of those grid cells is a neuron, and they are six-sided cells, and that means that information can, say from neuron 13 right there in the middle, information can flow across the boundary of neuron 13 to each of the 6 neurons that surround it. And so if neuron 13 wants to move a distance in a certain direction to go toward where he thinks there is the combination of attributes that are needed, he needs to find, then those 6 companions also move in that direction, but at a smaller distance. I think, I may be wrong, so don't hold me to this, I think Paradise software lets them move like 1/3 of the distance that number 13 moves. And then, of course, if 19 wants to go a different direction on the next, what we call epoch of training, why it wants to drag 13 with it in that direction, and so forth. So these guys are really pushing and shoving and trying to fight their way through data space to find the attribute conditions that they want to belong to. Now then, look on the right, and at the top you'll see I have a comment there that neurons number 1, 11, and 21, they define the downgoing direct P. And all 3 of those neurons are in the leftmost vertical column of this neuron map. So advance again, Laura. All right. On the black screen at the bottom on the far left, that's where neuron 1 found its family. And I believe there were like 174 data points along that white trend there. So what we're looking at here are the VSP data. The horizontal axis will again be depth increasing. The Earth's surface is at the far left of the horizontal axis, and the deepest receivers at the far right, and then travel time for the VSP data, that's the vertical axis, all right? So you're looking at that down sloping white line, that's a part of the downgoing P first arrival, which is an event I already referred to as the direct P. All right, now that we go to the center panel and we add neuron 11 to neuron 1, and you can see that that white line has increased in thickness. And now then go to the rightmost panel and we've added neuron 21, and it has thickened and widened the line even more. And so in combination, those three neurons do only one thing, and they build the downgoing direct P first arrival. Advance again, Laura. And what we will see when the next screen comes up, the neuron family that we started with, but now then look at what is written in the black font in the lower right, saying neurons 3, 12, and 23. They define P reflections and also P multiples, okay? So advance and let's see how that works out, Laura. Okay, far left, that's what neuron 3 finds. And now then, the first downgoing event sloping down to the right, that is later in time than the downgoing P arrival. I need to make a better quality display of these. It probably in color and had some numbers on the axes that'll help people see some the evidence of what I'm now saying in words. But you're beginning to see evidence of very weak evidence of some upgoing P reflections. And let me make a comment here. You know where the near field zone would be? That would be in the extreme upper left corner of each of these three black screens. And notice how black that is. These neurons said, hey, boss, I'm not going in that spot. I cannot get in there. And that's the near field zone. Now then, as you add neuron 12 in the center display, you can see that you add more evidence of downgoing multiples in particular. And then you add neuron 23, and it continues to build the downgoing multiples. And if you look real closely and spend some time, you can see that upgoing P reflections are also getting built pretty boldly when 23 adds its contributions. So Laura, advance one more time. And we're going to now look at these tables again. And so let's go to the top about the downgoing P first arrival. And there are those three neurons that we use to show what those three neurons are defining, 1, 11, and 21. And now then, if you look across each row, you will see the attributes that belong to those neurons. You know, all I've been saying up to this point is they wanted to find certain neurons that had certain amounts of that neuron energy involved, but I didn't tell you what neuron it was, nor how much of a contribution that neuron made to influence that. That attribute made to influence that neuron. But Paradise software allows you to see that detailed information. So now it's where you're really looking at the fabric of the downgoing P illuminating wavelet at the top, and down at the bottom you're looking at the internal fabric of the P reflections, and you see what neurons are. I'm getting neuron and attributes entangled in what I'm trying to say. You see what attributes are involved in each of those neurons and how much of each attribute is involved in defining that neuron. And on the right, you can see how many data points each neuron found where it thought it had a home. It may be helpful to kind of look at those rows of attributes and their percentages as sort of being like the DNA of that neuron. You know, hey, this is me. And so I found a neuron 1 up there at the top. It says, when all my family got together, we all had the same DNA. There's 174 of us. Okay, Laura, advance again. We're getting really close to having to shut this down. And This goes a little bit farther into detail here, that it's looking at the illuminating P, at the neuron structure, and the reflected P and the multiples. And the tables that we have looked at up this point, I only had 3 attributes listed because the table got too complicated if you went farther than that. But there actually were 4 neurons that contribute to the illuminating P, 5 that contribute to reflected P, and 6 that contributed to multiples. And so then I look at those, rank them from in the columns, rank them from most important to least important. And when the number in parentheses, which is giving you a percentage number as to how much they're contributing, that attribute is to all 4 of those neurons. So you see what attributes are important and how big their contributions are to these neurons that are building the downgoing illuminating P. Where I have the X's drawn across, that is a place where, if you read down at the bottom, the contributions above and below that X line diminish by at least 40% and more. And so what you see now, though, is that notice the equivalence here. Still, if you go across, sweetness, Hilbert, there's still a lot of equivalence in the attributes of illuminating P, reflected P, but there are different percentages of them and different orders of their importance. Advance again, Laura, got 1 or 2 more slides. Okay, here's your conclusions. Number 1, the instantaneous attributes allow you to backtrack direct S to its point of origin at the base plate, even if those shallow geophones are inside the near field zone. And direct P and direct S wave fields, they have the same major principal components. That's a little bit of a surprise. And then the last is that specific neurons build only the downgoing direct P. Other specific neurons build only the P reflections. So this is what you start gaining from unsupervised machine learning, and all of it in combination is showing you the fabric of the data. And all of this SOM analysis, we've only looked at vertical geophone data. Hadn't had time, to look at horizontal geophone data, but I'm eager to get with that, and I'll share what I find with people. I think, Laura, there may be one more slide I'll just make. And so if you're interested in what's going on, certainly stay in touch. You can find my email address either probably on the web, or you can find it through Geophysical Insights, because what I'm listed here is where I'm going to be going with this. Got to do the same very detailed analysis with horizontal geophone data. Got to go from zero offset VSP to far offset VSP. I've got to look at shear wave generated by horizontal vibrators and compare them to shear wave generated by vertical vibrators and by impact sources and buried explosives, and then go to different propagation media. So with that, I'm going to step back, Laura, and call this done. And I probably look like I've eaten up almost all of the time, but you please send questions. Geophysical Insights will find some way to get that to me, and I will be pleased to share with you any insights, advice, or whatever, listen to complaints and challenges, whatever you want to do. So thank you very much.
If we have like 1 more minute, we can stay on here before we've got to shut the meeting down for our next meeting. But if you have any questions, you're welcome to go ahead and enter them in the chat now. If you're watching via the YouTube live stream, you can put your chats in the comment section, and we'll be sure to get those. And Bob can respond to those verbally here in just the next, let's give it like 30 more seconds. Okay, well, if there aren't any questions, then I'd encourage you to hop over to our next presentation of the day, where Deb Sakery is going to be presenting some of her case studies. Thank you very much for attending, and we'll see you all shortly. Bye-bye.
Thank you, Laura.
So go ahead and start.
Yeah. So,
Okay.
well, here, I'll go ahead and
Oh,
introduce
you're okay.
So good afternoon, ladies and gentlemen, whether you're joining us here on Teams or on our live stream channel. Glad you could join us today. Carrie Loudon will be discussing calibrating SOM results to wells, improving stratigraphic resolution in the Niobrara. If you have questions during the talk, you're welcome to post them in the chat section of Teams or in the comment section of YouTube, and Carrie will be able to answer those verbally at the end. So without further ado, go ahead, Carrie.
All right. Thank you, Laura. Good afternoon, those of you. I'm not all that used to talking into my screen, but thank you for attending my talk today. I'm presenting a case study for an unconventional reservoir from the US, which illustrates how self-organizing maps can push the limit of seismic resolution to single sample, and how we can take these results and use our wells to validate the machine learning results. So the outline of my talk today, we're going to start with a little bit of discussion around why use machine learning, what does it bring to us that we didn't have previously. I'll take you through some examples of how attributes, sampling, and self-organizing maps can resolve geology below tuning. Then an introduction to the Niobrara petroleum system in the Denver-Julesburg Basin. And follow that with our multi-attribute machine learning interpretation thought flow, which is comprised of two pieces: the principal component analysis, followed by self-organizing maps. And then present the results of SOM on a Niobrara seismic survey. And we'll look at those results visually, and then look at how I took those results at the well locations and calibrated our SOM, and then finish up with some well to SOM statistics. There we go. So why do we want to consider seismic multi-attribute analysis? The seismic attributes have been around for decades, and they've always been very challenging to interpret because they're responding to a complex subsurface that's a combination of lithology, fluids, pressure, stress, faults, and fractures. And there's never really a single attribute that tells us this is it. We can interpret this one attribute. So we've always been trying to interpret multiple attributes. And what does machine learning bring to our task of interpreting seismic attributes? It helps us to address the overwhelming task of interpreting dozens and hundreds of attributes. So seismic data has always been a big data problem in our industry. And machine learning addresses the human inability to visualize attribute relationships beyond 4 dimensions. So as humans, we can easily see 2D or 3D cross plots, and we can add color. But beyond that, we cannot see relationships in 4 dimensions. However, a computer does not have that limitation. And then over the last few years, computer power continues to evolve exponentially, and new visualization techniques. For example, in Paradise, we have a 2D color map, so there's additional visualization techniques that have come to the forefront as well. But ultimately, our motivation in considering multi-attribute analysis is to produce better subsurface interpretations, reducing our risk, and hopefully for our clients, allowing them to make money, whether that's drilling better wells or leasing better acreage. So today we're going to look at unsupervised learning, but if you were to Google machine learning, you'd see these 4 categories, our 4 main categories of machine learning. So let's take a brief stroll through these. Supervised learning is really the most popular method in our industry. It takes a set of known input data and trains a model to apply new data to predict a result. An advantage of supervised learning is that you get directly to a specific answer. For example, you might get a porosity model from pre-stack inversion, and that's been trained to well data. Unsupervised learning, however, is quite different, and it does have its own advantages. Unsupervised learning has no a priori knowledge of the data it's organizing. The training adapts itself directly from the data. An advantage to this is it finds patterns in the data that might not exist in the training data that's used for supervised learning. And we see this quite often in our unsupervised machine learning projects. And toward the end of the talk, I can kind of point out some of the reasons for this. So supervised learning can be thought of as a task-driven approach, and it's predicting the next value from a set of inputs, whereas unsupervised learning is data-driven and is a means of finding patterns within the data. Then our other two types are semi-supervised learning, which is a simple combination of the two. And lastly, reinforcement learning, which is when an algorithm learns over time to maximize returns based on rewards it receives for performing certain actions. So the case study today is going to be on unsupervised learning. So the next section is going to go through a little bit of how and why self-organizing maps can help us discriminate or resolve thin beds. SOM classification is simply a method that uses attribute space to classify seismic samples. So in this example, we just have a cross plot of two attributes, and they've already been marked with their symbols into which cluster they fall into. So the SOM process simply introduces natural clusters in attribute space and introduces multi-attribute samples called neurons, and the SOM neurons will seek out the natural clusters of like characteristics in the seismic data. And the neurons learn the characteristics of the data cluster through an iterative process of cooperative followed by competitive training. And when the learning is completed, each unique cluster is assigned to a neuron number, and the samples are now classified. Another important concept in Paradise is that we use sample-based attributes. So every sample from every attribute is put into the SOM. We don't use a wavelet-based approach. So this example is just showing you how instantaneous attributes at the sample scale look for about, I think this is about 100 milliseconds of data in time. So in attribute space, this would consist of 7 dimensions. And this is going to take you through a synthetic example that is really, I think, a powerful illustration of thin bed discrimination by self-organizing maps. So in this model, we have an RC series on the left, I believe 2 millisecond sample rate. We have a sort of thick positive acoustic impedance followed by a single sample trough peak, each one sample, a peak trough, each one sample, and then a slightly thicker trough. Now this RC series was convolved with a wavelet to create traces, and then these were duplicated to 100 traces with noise added. And here on the left, we simply have a cross plot of the Hilbert transform versus the regular amplitude. And you can see that clusters are very apparent in this simple cross plot of the data. Now, if we run this through an 8x8 SOM process, you can see each of these clusters is assigned to one of these 64 neurons in the SOM 2D color map. Now, taking this back to our original time series, you can see in the example that each of our events in our original RC series has formed a unique cluster within the SOM. And so cluster neuron 57 is our sort of thick high acoustic impedance layer. It's actually separated the negative amplitude from the positive amplitude in 8 and 55. So there's one doublet pair, and then 28 and 33 are a second doublet pair. And then our other higher acoustic impedance layer number 9. So I hope this convinces you that the SOM process is able to distinguish very thin layers within a seismic time sequence. So in a practical case, how does this work in a 3D cube? I'll just take you through an imaginary 10 attribute example. So we have a 3D amplitude volume in survey space. And if we were to compute or select 10 attributes to go into SOM, we might have started with 20 or 30 attributes, but we've selected SOM, and each sample in the 3D cube will also have 10 values associated in X, Y, and time in attributes. And we take those attributes into attribute space. So now we're in 10-dimensional space, and we run that through the SOM classification process. And the SOM will perform cooperative and competitive training, and in this case, classified to 64 patterns. Now that's not set in stone, that's up to the interpreter. We offer a very large number of potential SOM topologies. 64 is one of our favorites. Once the data are classified in attribute space, it goes through a nonlinear process to map those SOM neurons back to a 2D color map. And then each of these neurons is also placed back into the 3D volume. So you end up with a 3D volume back in survey space where each sample is classified as one of these neurons. And then once you have that in a 3D volume, you can start to interrogate it and interpret it. So that's the SOM process in a nutshell. I guess I said that. I forgot to put the words up. Okay, so now we're going to look at introduction to the case study. Our case study is out of the Denver-Julesburg Basin. The Wattenberg field, here's Denver for reference. The Wattenberg field was produced originally as a basin-centered conventional gas reservoir down in these Dakota sands. Our study area is up here in the northern part, almost near the Wyoming border. And so this is an asymmetric foreland basin, covers approximately 70,000 square miles over parts of Colorado, Wyoming, Kansas, and Nebraska. The basin has over 47,000 oil and gas wells with a production history dating back to 1881. However, until 2009, it really wasn't being drilled with highly deviated wells. Most of the wells in the basin at that point were vertical, so they were drilling without seismic. Starting around 2009, so 11 years ago, the operators in Wattenberg began to drill and complete horizontal wells within the Niobrara. And we have a cartoon here showing the strat column. All of these are pay zones. The shales that are source rocks are shown here, and the Niobrara is kind of blown up. It's a typical depth. I should mention this is from Sonnenberg, a professor at Colorado School of Mines, taken from one of his publications. So there are these chalk benches within the Niobrara, and they're informally termed the A, B, and C bench. And those are the primary reservoirs for the horizontal drilling. And they're interbedded with very rich source rocks. However, when the horizontal drilling started, they found they were hitting a lot of structures and faults that they weren't seeing in the vertical wells. So they quickly recognized the need for 3D seismic data. And beginning around 2015 or so, maybe 2010, sorry, GPI and at the time Geokinetics undertook a 1,500 square mile multi-client program in northern Colorado, the outline of which you can see here. And they provided geophysical insights with 100 square miles of this multi-client data to do a proof of concept on whether our self-organizing maps approach could improve the resolution of the Niobrara reservoirs. In addition to the seismic data, we had about 30 wells in the area, the 100 square miles that were available through the public COGCC database. And out of these, we selected 7, which are shown in red, to have a full petrophysical analysis run on. So the time structure map is shown here, north on the left for the 100 square miles. And we're showing the production is very closely tied to fracturing in the chalks. As you can imagine, it's a very low porosity reservoir. And the insets here are structural elements. This was from a study of the Austin chalk, showing the kind of fracture patterns to expect for various structural elements, most of which we have present in our survey. So here to the west, you can see you're coming up on a fairly steep fold as you're coming up to the Front Range of the Rocky Mountains. And the predominant faulting direction is, you can see from the time structure map, northeast to southwest, but that's also overprinted with a northwest to southeast fault pattern. This is on the top of the Niobrara. This is the most positive curvature. And so you can see a lot more detail on the complexity of the fault geometries and the 2 main fabrics overprinting each other, and how these would actually generate nice fracture sets within the chalks. And these attributes are computed from the AASPI consortium library that is provided with Paradise. Here's our original data, and it's very nice seismic data, very, very clean. We selected approximately 60 milliseconds. So the vertical scale on the left here is 2A time in seconds, and our trace spacing is about 110 feet. The seismic data we downsampled once from 2 milliseconds to 1 millisecond. The Niobrara is a fairly easy event to follow. The top Niobrara is a strong peak, shown here. The base of our study section was the top of the Greenhorn. So within the 60 milliseconds, we have our 4 reservoirs, the benches of the Niobrara, as well as the Codell sandstone, which I forgot to mention in the last slide. But the Codell is a sandstone that's also being produced from these horizontal wells, and it's a fairly thin, highly heterogeneous sandstone that is overlaid unconformably by the Niobrara Formation. We have a strong trailing trough that sits between the A bench and the B bench. And another thing to notice is how much more internal faulting there is within the Niobrara that you don't necessarily pick up if you're just looking at the very shaly part near the top of the Niobrara. So we're looking to see whether the SOM process can give us more detail on these 4 reservoirs within the 60 millisecond interval. Selecting the attributes that go into SOM is another very important step in the analysis, because as I mentioned earlier, we all have maybe our favorite attributes, but it's hard to put a direct physical interpretation onto a single seismic attribute. So how do we decide which attributes to run into our SOM process? And for that, we use principal component analysis. And principal component analysis is another unsupervised machine learning technique that helps us with dimensionality reduction. So it's a technique that will take a large set of variables and reduce it to a smaller set that will still contain most of the variation of independent information from the large set. So PCA helps us find the most prominent and important seismic attributes in our data. So Paradise allows us to do a pretty exhaustive PCA. And rather than go through how we do it, we'll go through some of the results. This is a PCA result from Paradise for the first 2 eigenvectors of our interval Niobrara to Greenhorn. In this case, we selected an inline that was going through one of our key wells, but you can look at all of the inlines in your survey, and you can look at suites of inlines in the survey to see if your PCA, how it changes throughout your survey and through various time intervals. So in this case, we ran it over a fairly narrow window, just our Niobrara to Greenhorn. And from the first eigenvector, you can see I kind of blew up because it's hard to read the chart, but we had 3 prominent attributes within the first eigenvector, and those are sweetness, envelope, and relative acoustic impedance. And you can see their relative their contributions to the eigenvector, and then it drops off quickly for the other attributes that we put into the PCA. Likewise, in eigenvector 2, we only had 2 prominent attributes, and those are thin bed and instantaneous frequency. So these 5 attributes, along with another 4 from other eigenvectors, are going to go into our SOM. But you don't want to just do this blindly necessarily. So it's always really important. You should inspect your attributes. You just don't want to look at the bar graphs and throw them into the SOM. So we took the additional step of trying to look at the sweetness, for example, at our primary reservoir, the Niobrara B. And likewise, we have the thin bed indicator extracted near the Niobrara B, near our primary reservoir. And you just want to make sure you don't have any surprises in those attributes. So ultimately, we selected 9 attributes from our instantaneous suite out of 6 of our eigenvectors, and these are listed here. So that went into the SOM. So looking at the results, here we have our original data through one of our key wells, one of the wells that we have the petrophysical evaluation on. And here we have our 8x8 SOM, which after doing a visual kind of QC of the different SOM topologies, this was the one I liked the best. So the one I tried to tie back into my wells. So the B bench is near the center up here on our amplitude section. It's this kind of faint peak, but in the SOM, it just jumps right out at you. It's this yellow, red, yellow sequence. And again, you can see there's a lot more structure on the chalk than there is on the seismic horizon that you're picking. So as far as trying to place wells, this kind of detailed image of your reservoir will certainly enable you to place your wells and understand how you're going to stay in zone. Zooming into the well, you can again see we have about 5 milliseconds of data covering the B, which I've blown up here. That's a total of about 30 feet in depth. And our bright red and orangey neurons actually are corresponding to the maximum carbonate content within that B bench, as you can see here. So the neurons in the middle of the B interval are actually showing you the sweet spot of the reservoir. And here's a reference for how these logs were calculated, if anybody wants to follow up on that. These guys have done all this from triple combo type wireline logs and come up with lithologies and TOC, etc. Here you can see our clean pay flag as well. Now this is a cross section through 3 of our wells with petrophysics, and there's a lot more to look at in this cross section, but I'll show you some of the highlights. We have our B bench here, and you can see the markers. Interestingly, the SOM images where the B is through some complicated structure. This area right here is very complex, and it's hard to pick what's happening structurally with the Niobrara as you take this down to the greenhorn. Likewise, you can see some areas where perhaps your reservoir has been faulted out. So you get a lot more detail out of the SOM that you can use to also avoid bad areas in addition to finding your sweet spots. The A bench, the base of the A bench is well resolved in the navy blue. And we also have our best source rock is this high TOC zone that's sitting above the B and below the A bench, and that's shown in this pink and blue neurons. The base of the high TOC zone is not resolved by the SOM, but the top of it is. So all in all, we get a much better picture of the stratigraphy from the SOM than we do just from using the amplitude data. So everything I've shown up to now was work that was done in 2018. I revisited this project after Paradise 3.4 got released because it came with the ability now to extract logs from our SOM results at well locations. So here's a cross section I built in Paradise through our 8x8 SOM and the 7 wells that we have the petrophysical results on. What we have on the left, the track 1 has got a V-shale curve and a gamma ray. In track 2, I've taken the SOM and I've also overlain it with the volume of calcite curve from the petrophysics. And then the third track is our TOC. The fourth track is effective porosity. And then the fifth track is resistivity. Because the reservoir is chalk, I think that the volume of calcite is a better indicator of reservoir than B shale. So when we move into the SOM statistics, we're going to use the volume of calcite as a cutoff. But another thing to note, we have our Fort Hays limestone down here near the base of our interval that we studied, and you can see that the SOM neurons could potentially be repeated. So it's important, you can export these logs as LAS files. And we had a summer intern named Yin-Kai Wang who built a statistical analysis tool to help us evaluate the extracted logs along with the other well logs in the wells. But it's important, in this case, I only evaluated down to the base of the Niobrara so that we weren't catching this Fort Hays limestone when we're trying to evaluate the SOM results statistically. Now this is from Yin-Kai's program that he wrote for us over the summer, and it's based on a paper that was published by Leal and others. If you want to see more on that too, we have Fabian Rada has presented in our booth this week. And they built something called contingency tables and produced statistical measures of the relationship between the flags that they applied to the logs. In this case, we used effective porosity and volume of calcite to flag reservoir versus non-reservoir just within that Niobrara interval. So I like personally just looking at the histograms. And looking at these histograms, you can quickly see that we have some neurons in our SOM that are dominated by non-reservoir. And then we have some that are clearly reservoir, and then we have some that are mixed. When you make this contingency table, you get a measure called chi-squared, which shows you whether there is a relationship between your SOM neurons and the flag that you've set, in this case, non-reservoir versus reservoir. And in this case, the chi-squared measure on the 8x8 SOM is saying, yes, there is a relationship between SOM neuron and the presence of reservoir or non-reservoir. So that's going over the entire Niobrara interval. Going back to Paradise, I looked at these in 3 dimensions and tried to get a feeling for whether the neurons vertically and laterally were present throughout the various benches, through the various reservoirs. So here is our A bench. So our extracted log tells us these neurons are present in the wells, and it shows us which of these neurons have reservoir. Some of them are almost exclusively reservoir, and some are non-reservoir. The chi-squared measure shows us that there is a relationship. And then looking in the 3D viewer, you can turn on just those neurons that you found at the wells and look at how they are stacked both vertically and laterally within your 3D volume. So you can see these these neurons are concentrated near the top of the formation. I actually think 15 and 16 are part of the shale, but of course, the time to depth conversion can sometimes pick up a stray here or there, a stray hit count. Looking at our B bench again, and this is kind of neat to see that your neurons are fairly well clustered in the 2D map. So these are all the neurons that are in the wells at the B bench. And again, the chi-squared test failed. And in this case, it's not because there isn't a relationship. This is really because we have very few neurons that are actually sampling non-reservoir. The B bench is almost entirely reservoir. And so in this case, the histogram is probably more helpful than necessarily the chi-squared. But if you go to my colleague Yvonne Marakin's talk tomorrow, you might be able to find some other measures besides these to look at the statistical relationships. And then moving on to the C bench, again, we see a different cluster or set of neurons that are sampling our C at the wells. And again, we can see that most of the C bench is reservoir as well. So this is really helpful to be able to map out in very fine detail over the three-dimensional volume the presence of these neurons. So that's one way to calibrate your SOM results to your wells. Another question we looked to address this summer with Yankai's work was, I think I mentioned that I just selected based on my visual inspection of the SOM was the 8x8, but he's actually found a way to measure, since we can measure chi-squared, also likelihood ratio, Kramer's V, and Bayes factor, all computed from these contingency tables. You can look at all of these different SOM topologies and what's happening at the wells. And you can see that the highest chi-squared value is the 8x8. I apologize, this is hard to read, but we have 4x4 on the left and 12x12 on the right. So each one of these measures seems to suggest that the 8x8 topology is the best, at least over that top to base Niobrara section. And certainly you could look over the whole SOM. You could probably apply some different cutoffs, etc. And one thing I've decided about this particular SOM after looking at the extracted logs and looking at the log curves we had available is it's really discriminating between carbonate and shale. So it's a lithology discrimination SOM. And we can use the SOM to map out the chalk benches. We could probably also use it to map out the shales. And I didn't really go into detail on what's below the Niobrara, but I'd like to take that on next, is looking at how it does with the Codell sandstone. So to wrap up, one thing that you do have to be careful of is, and this kind of goes with supervised classifications as well, is we had 7 wells in 100 square miles, and we extracted seismic data at those wells and produced hit counts of what neurons got sampled at that well location. So on the left, this is from Petrel, is the full histogram for the 3D seismic SOM. This is a 7x7, not the 8x8. But the statistics for the full 3D volume for the Niobrara B bench on the 7x7. And in this case, you see that 45 of 49 neurons in the SOM have data within the seismic volume. But if I take my 7 wells, we've actually only sampled 19 of those 49 neurons. So it's important to look at the statistics of your full survey in addition to what's happening at your wells. And it might be that some of these neurons are not really in the zone of interest. There might be something wrong with your horizon or the way you've isolated the zone or something. But when you go back into Paradise and turn on only the 19 of the 49 neurons that our histogram says are the B bench, and then you look at that in 3D and you do find holes right smack in the middle of the B bench. So it's definitely worth going back and finding out what those neurons are, how extensive they are in your volume, and maybe looking for additional wells that might sample these neurons, and they may show you something different if you can find a well that has sampled that interval from the ones that you sampled up to that point. So it's important to consider the volume as well as the well statistics. So that's just a watch out. So thanks for your time. I'll wrap it up and then we'll take questions. So in summary, seismic multi-attribute analysis is delivering on the promise of improving interpretations via the integration of our attributes, which respond to subsurface conditions, such as stratigraphy, lithology, faulting, fracturing, fluids, pressure, etc. Statistical methods and SOMs enhance the interpretation process and can be easily utilized to augment traditional interpretation and utilizes attribute space to simultaneously classify suites of attributes into sample-based high-dimension clusters. And in the DJ Basin, we have used SOM to resolve our primary reservoir targets, the Niobrara chalk benches. And these are found within approximately 60 milliseconds of 2A travel time data. And we've resolved our benches to the level of 1 to 5 neurons, which in depth would correspond to anywhere from 7 to 35 feet in thickness. And the Paradise visualization tools, including 2D color maps and well log extractions, enable closer ties to our well data, which is bringing a lot more value to the results that we're producing. So quick acknowledgements, really thank GPI and Fairfield to let us use this data and such a nice high quality data set. I have to acknowledge Inkai for the program he provided that lets us apply the statistics to our extracted logs. Sarah Stanley and Patricia Sanagrossi did a lot of the work on this 3D volume as well. And Digital Formation for providing the petrophysical analysis. And that's it. Now I have to find my chat box.
It's totally fine. I got this, Carrie.
Okay.
If you want to avoid switching back and forth, then I can just read you the questions as they come in.
Okay,
Again,
great.
You know, for our audience, you're welcome to put your questions either in the chat box of the meeting here, or if you're watching via YouTube, you can put it in the comments and we'll get those and then read them to Carrie and she can respond verbally at this time.
And also, I'll be in the Meet the Experts room after this too, if anyone wants to just have a long chat
Yes,
with any of my colleagues.
True. Yeah, let me make a little plug here real fast. So if you're in our microsite for our SEG booth, there's a link that says Meet the Experts. And over there, I think are about 4 meeting rooms where we have our staff who are hanging out and standing by and ready to talk to you, have a virtual cup of coffee, give you a demo of Paradise, whatever. So you're welcome always to drop in there and say howdy to them. So, and I think Carrie's referencing, she's going back over into there. And I think, I'm pretty sure, Carrie, you're in the one called Geoscience Applications. Is that correct?
That's correct.
Yes. So you're always welcome to go meet her over there if you have just an exorbitant amount of things to talk about that don't fit in the chat box. Let's give it another couple of minutes here. Okay, Harry, you're always welcome to go over there and read your many accolades on your presentation, but I'll save just reading the questions for now.
Okay, great, Laura. Thank you.
I think we're good. So again, if you want to visit with Carrie, you're welcome to head over to Meet the Experts. Stay tuned. We have Heather Bettel presenting here momentarily from the University of Oklahoma. So stay tuned for that. You'll just go into the live presentations, go to Heather Bettel's presentation and click Join Now. We'll start that in about 15 minutes. Thank you very much. We'll see you all soon.
Bye. Bye-bye.
All right, so we'll give it maybe another minute and wait for people to join, and then we'll get started.
That's fine. I will warn you, my internet's already flicked out a couple times in the last hour. So
Oh dear.
it happens all the time. I live in rural Oklahoma.
I
and
see. I get
There's
that.
only one internet provider, and for some reason the hours between 2 and 4 seem to be the worst.
Yikes.
So I don't know if it's like because a lot of the schools are virtual, and just the infrastructure. And since I'm out in the country, I guess everybody gets preference besides me. Who knows? But that's why I call it on my cell phone. But like sometimes my cell service flickers out too. So
Yeah, I get that.
In the beginning of the semester, or I guess in the spring, it used to make me nervous when my internet or cell service would fail, and now it's just another thing I deal with.
Understand. Well, hopefully these days will be behind us soon enough.
Hopefully. I'm teaching online in the spring, so
Right.
I'll have to deal with it then, and my kids will still be homeschooled in the spring. So.
Indeed. Well,
Yeah.
it's 3 o'clock, so let me go ahead and get started.
Okay.
You ready?
Sure, I'm ready.
Okay.
So I should go to the first slide.
There you go. Go to the first one. All right. Ladies and gentlemen, welcome to our talk today. Heather Bettel is going to be presenting on gas hydrates, reefs, channel architecture, and fizz gas, SOM applications in a variety of geologic settings. If you have questions during the course of the presentation, you're welcome to go to the chat box if you're in Teams and type them in there. If you're watching via the YouTube live stream, you can type your comments into or type your questions into the comment section, and we'll get those as well. At the end of the presentation, I'll read those off to Heather, and then she can answer them verbally. So without further ado, Heather, go ahead.
Hi, everybody. I'm Heather Bettel. I am an assistant professor at the University of Oklahoma. This is my beginning of my 3rd year there. And the University of Oklahoma is lucky enough to have some academic licenses for Geophysical Insights Paradise software. So I thought I would show a couple of case studies that my graduate students have been working on. So I'll be showing some work by Julian Shannon, who will be getting his master's in December, I hope. Corellia Lamarca and Carol Buist, who both got their masters in the spring and are continuing on with me for their PhDs. So I've got 4 case studies that are a little bit further along than some other studies, and I'll just go over them for, about 10 minutes each or so, just to show you some of the variety of what we're trying to use SOMs for. So I'm going to start off with gas hydrates. This is work Julian Shannon did for the first part of his master's. And to kind of give you guys an intro to gas hydrates, so gas hydrates are where you have a methane molecule trapped in an ice structure. These form in different pressure temperature conditions, a lot of times on the continental slopes or in the permafrost. And so they tend to occur in the area that we're looking at in New Zealand. They tend to occur between the seafloor and, well, you can see a nice DSR right here. Okay, and so you'll have these gas hydrates forming in the pore space, and what's interesting about them in a hydrocarbon sense is that they can act as seals and traps for larger hydrocarbon accumulations, which is thought to be causing some of these bright reflections here and over here. And so what I got curious about, and what I got Julian curious about, was thinking about, is there a better way to image these hydrates? Because we aren't able to see them in seismic data, but rather what we see is what we call the BSR, or a bottom simulating reflector, that ends at the base of the gas hydrate stability zone. And I know you guys can't see me because I don't have a video on this computer, but I'm like using my hands to demonstrate, and I should use the mouse. So this is an example of a BSR. So you have the area from the seafloor down to a certain temperature pressure where the gas hydrates are stable, and in that solid ice kind of formation below that, they act as fruit gas. And so when you go from an acoustic impedance regime where they are stable to where they are unstable, you get a larger reflection coefficient, which reflects the seismic energy back up, and that forms what we call the BSR. And so this is an example schematically of what that would look like. But what's interesting is that not every area where we have hydrates on Earth do we image a BSR? And so particularly in the Pegasus Basin of New Zealand, so here's the North Island and the South Island, and then here's the Pegasus Basin, and in pink I'm showing you the line that we're looking at right here. In the Pegasus Basin, it's really, really interesting. It's well studied. There's some 2D seismic there. I hear there's some 3D, but I haven't gotten my hands on it yet. But you can see that in some areas you have a nice strong reflector, a nice strong BSR, and in other cases maybe you see it. It depends on how you squint or not. And so we're curious, does that mean that there's no hydrates in this area, or is there just no free gas below the hydrates to let us see a strong BSR? And so we thought this would be one of our first examples where we tested out SOMs to see if the SOM results with the multi-attribute analysis would be sensitive to perhaps some of the attenuation or frequency changes that are happening in the areas where there's hydrates. And so here's a nice slide that Julian put together. We're working, like I mentioned before, in the Pegasus Basin. We actually have two 2D surveys in this area, the PEG-09, which is shown in red, and then the APB-13, which is in a tighter 2D grid. And so this was a great case study for us because we could run SOMs on the PEG-09 data and then see if we could replicate the results on the APB-13 data that was shot like 4 years later. And so this is Pliocene sediments, kind of zoomed out. You can see the Pacific plate subducting underneath I think it's the Australian plate, and we're kind of in this frontal anticline area where you can see the BSR. And we've got, if you zoom into this blue box, we've got nice strong BSRs here and here, and then these weak discontinuous BSRs that we're super curious about between those two. And so for the workflow that Julian came up with, the first thing he did was he imported the data into AASPI, Petrel, and Paradise, ran some attributes, tried to understand in his mind what was going on, and then move all of that into Paradise to run a PCA to see which were the more important attributes that should be used for the SOM analysis. After that, he tried to optimize the parameters, looking at the number of attributes we should run, the number of epochs, the number of neurons, that type of information that you guys are probably familiar with. And then he did some mapping. And what he did in the Pegasus Basin after that was, with the results, he mapped where he could see the BSR with the traditional amplitude interpretation, so the regular amplitude data, and then also with his SOM enhanced interpretation. And then we'll talk about some other results also later on for the last case study that he did. So like I mentioned before, if you have hydrates present, you can have different reflection coefficients happening depending on if there's free gas below them or hydrates above them. So if you have a high amplitude BSR, typically in this area, you have the hydrate column above it, free gas below it causes a large drop in the reflection coefficient, so you get a nice bright amplitude. In the areas where you have a weak BSR, we think the reflection coefficient is much smaller because you don't have that free gas below it, minimizing the acoustic impedance in that area. And then in the area where there's no hydrates, you wouldn't expect to see any reflection because there's no change in the acoustic impedance between the sediments above it and below it. There's no hydrates in the pore space. And so we were able to look at these results. We had some angle stacks, but not gathers. So Julian was also able to run some ABO attributes like flow factor and instantaneous gradient and that type of stuff. And so just to kind of get to the results, here we're looking at the Pegasus line 19 that I had outlined in pink on a previous slide, and kind of the weak BSRs are in this red box. And so you can look at the seismic amplitude and then the raw results in the SOM, which of course hide what we may be interested in. So we just turned on a few neurons that seemed most interesting. And here's some of the results from the different neurons, which I have the attributes that go into them that I'll show in a few slides. But we noticed that a couple areas seem to be highlighted here. And so what Julian ended up doing is, we thought, okay, things seem to be working well. Let's try to optimize our SOM. Optimize meaning the number of epochs and neurons that we're using, as well as the different attributes. And so here's a case where we have an unoptimized SOM. So we're running, what is this, like an 8x8, it looks like. And then down below in image C, he just turned on a few of the neurons that seem to be most revealing and in the region of the expected BSR. And so we're pretty excited about this because it seemed like this red neuron number 50 seemed to be highlighting where there could be a very weak or discontinuous kind of indistinct BSR. And so after that, he optimized the SOM, cut down the number of neurons, the number of attributes, and got this result shown here down in F with just 3 neurons turned on. And so we're thinking that this is one way that we may be able to help distinguish these very weak BSRs. Looking at 2 intersecting lines, kind of shown up here in the upper right-hand side, we've got line 6 and line 19, some green arrows to highlight the strong BSRs, which clearly show up when you look at all the neurons, and then just turning on the few that we were interested in. And while you see some other stratigraphy in the area of the weaker or discontinuous BSR, we do see that these neurons seem to be highlighting a feature that could be that hidden BSR. Like I mentioned before, we had a second seismic survey, the APB, that's in the same area. And so we wanted to see if we could take this technique and the same parameters and get a similar result, like a reproducibility of the science and the method. And so this is looking at 2 inlines and two 2D lines that are perpendicular and in the same area as the one I just showed you. And so using the same method, he was able to replicate some of the results kind of shown here, where the weak discontinuous BSRs are highlighted by the orange arrows. And so we're pretty optimistic that the SOM method is giving us some good results to help image the BSR. Just a few notes on the eigenvectors and the attributes that helped out. You can compare the Pegasus 09 with the APB 13 and see that the instantaneous and the thin bed were high contributors in our SOM analysis. The other ones that we used were sweetness, the gas indicator, and the Shuey fluid factor, which are AVO attributes. And so overall, our takeaways were that the PCA results for both models were nearly identical, with just small discrepancies. So that's great for reproducibility. The SOM clusters that seemed to highlight the weak discontinuous BSR were identical. And so we were glad to see that this method was transferable between 2 surveys in the same basin. What he did next was he mapped a traditional amplitude interpretation, just mapping on the full stack. And so where he saw the BSR with confidence, interpretation confidence, he mapped in red. And then you can see in yellow are areas where the machine learning SOM method helped him extend out where he thought those hydrates could be located with that weaker BSR. And here's all the text that goes with it. So we're pretty excited about this result and being able to use SOM analysis to help us better map BSRs related to hydrates in New Zealand. So the next example I'm going to quickly show is looking at some pinnacle reefs, and this is some work that my student Carl Bulis was doing as a master's, and he defended in the summer, and now he's working on finishing up this study, adding in some few more details in order to create a manuscript out of it. So up in the Michigan Basin of the United States, there are quite a few pinnacle reefs Devonian in age, and we have access to a couple of small, very small seismic surveys that have been shot in the last 5 years or so by Consumers Energy, which is a natural gas company. Carl, for this work, focused primarily on the Putty Gut 3D data, although he did look at IRA and Lennox, but I won't be showing you those results just for time today. But again, he developed a method over Putty Gut, and then he wanted to make sure it was transferable to IRA and Lennox, because I like to teach my students that science and methodology should be transferable. So here's a zoom in of the Putty Gut reef. This seismic survey was shot in 2019. We have pre and post stack migrations. There's a couple of 18 wells or so, no, 30 wells that have gamma ray, 18 wells that we have core descriptions, and then 5 where he had core profile data. We were given formation tops and some horizons from Matthew Ryan, who works for Consumers Energy and helped provide us with this data. And so here's just the time structure map of the reef, and then what it looks like in seismic data. And so what I'll be talking about, for the next 5 minutes is how Carl tried to use SOM analyses to see if he can come up with any ideas about the internal structure of the reef. Do the SOMs provide us with more information about the internal structure and facies than just a single attribute analysis? The company, Consumers Energy, they're of course interested in porosity and permeability, and the SOMs could help us with that, which we didn't quite get super definitive data for. Oh, you guys lost my PowerPoint? Uh-oh. Well, hopefully it comes back up. I have bad internet. Oh man. Okay, but so anyway, so Consumers Energy wanted us to see if we can have any ideas about what's going on with porosity and permeability, and that we weren't super confident in the results for, but we're still working on it. Let's see let me mess around with this really quick. Let me try stop sharing. I'll open the share tray and try to get this back up. You guys, I got cool science to show you. All right, Julian, type in if you could see it. I hope you can. Any luck? Okay, well, I'm just going to keep talking, I guess, since I can't tell if you guys can see it or not.
Hey, Heather, Heather, we can't see it. Do you want to try sharing it again?
Okay, I just tried. Let me stop sharing. And then I will open the share tray. I will open back up the PowerPoint, hit share. Okay, it says it's sharing it. Do you see it?
It looks like it's thinking about it.
Thinking about it? Okay.
Sometimes, like especially with a slow internet connection, it takes a minute for Teams to register your screen.
Okay, well, I'm looking at, I don't know which was the last slide you saw.
Tell you what, if you want to, you can just send me the PowerPoint real quick, and I can throw it up on my screen, and you can talk to it if you want.
That sounds like an innovative idea. Let me try that. Let me put up my email and get this going. Oh, this place is good. Pandemic, working from home.
Pardon us, folks. Bear with us one moment.
Yes, sorry, guys. All right, let me send this to Laura. Let's see. The Advertis
Yep.
email, is that right? Okay. Yep. And it is only probably too big for me to send to you. Yeah. All right, that's not gonna work. Well, if you guys give me 2 minutes, I'll put it up on my shared drive, and then I could send you the link to it,
That's
Laura.
fine. We could do that too.
Okay. And it's weird because it seems like my internet is actually working. Maybe not. Nope, it's second. Oh, no. Yeah, so that's not going to work. Huh. Let me just try one more thing. Unfortunately, if my internet's slow, it doesn't want me to sign into. Oh, here I am. I'm on OneDrive. I'm copying it now, and I appreciate everybody waiting.
It's a weird new world for everybody.
I know. Like I said, this used to like frazzle me a lot, and now I'm just like, oh, it's another day. I teach my lectures, and I just lecture without slides, and tell the students to look at the slides later. It's like almost 100 megabytes, so it's taking a minute to upload.
That is just fine.
For me to send you the link, because I have so many awesome pictures in here. And then I'm just going to try refreshing and sharing one more time. Oh, wait. While it tries to load. See, if I was really cool, I would have like come up with jokes or stories to share. All right. That's still uploading. Well, maybe I just won't share the last case study because I run short on time. All right, here it is. I got the link. Copy link. Copy, and now I am emailing it off to you, Laura.
Great.
So hopefully you can access it. And then you can share it and I can talk.
And if you run long, I'm the one talking after you, so it's fine.
Oh, okay. Well.
All right.
I told my kids they can't bug me until 4 unless the house is on fire or they have to go to the hospital. So. And then I was on about slide 19. And I just won't be able to, I guess, point out cool things. I'll stop sharing.
I'll try to help you out best I can. All right.
Okay.
Got it. I'm sharing my screen. Give me just a second.
Okay.
All right. It's showing, but it's loading. Give it a second. That's a really big file to load. So
yeah. And
there we go.
And it looks like Julian and Corellia are in this meeting, so if people have questions, they can also ask them because they know all the nitty-gritty details. Carl cannot attend because he's teaching my lab right now. Okay, so as you guys can see here, and I'll just tell you to go to the next slide. This is the workflow, a very simplified workflow that Carl came up with to work his way through those reefs. The first thing he did is, student projects. You gotta teach you guys all the right stuff to do. So you load the data and you do QC work. You try to understand what's going on. I look at the files and the headers and see if there's footprint and all of that super fun stuff. Next thing he did was run single attributes, which I'll show you, and then he did some well ties to try and understand what the attributes were telling him about the physical rock properties. He wanted to do a mini study looking at what happens in a SOM analysis with geometrical attributes as compared to more frequency-based attributes. So I'll show you 2 different SOM results. And then he did like the PCA analysis and created what he calls his best SOM, where he compared that to the wild data to try and understand the relationships between the rock properties and the neurons. And so I've just got a couple of slides on this project to show you. So if you want, you can go to the next slide. And so what he did is he did this for the putty gut data, and then he also compared it to 2 other reefs, which I won't show you for time reasons. All right, can you go to the next slide, Laura? Or did you? Okay, so here I'm not going to focus on this too much, but here's some of the single frequency attributes that Carl selected on the brown horizon through the reef. And you can see clearly, you know, even on like the two-way time map, where you have the reef and the non-reef structures. And then he looked at some different amplitude and frequency attributes, tried to look for features in different frequency domains. I've got a little box covering it, but I think it's like 29, is it 29, 57, and 81 hertz. Next slide, please. So here on the next slide, I think I'm lagging a little bit, but are the Pettigut well correlations with the SOM. Hopefully you guys can see that. And so what we have here are some of the well data, and then he plotted on it some of the main neurons, and that's kind of in the center box of the well. And so what he noticed in the neurons that he was looking at in particular, that neuron 23, which is the bluer color, the dark blue, tended to show up in areas where he had the highest permeability and porosity. And then two other neurons that you can see in the left well in those yellow boxes were neurons 10 and 25, which he found consistently in areas where there was what he classified as good to great porosity, but then varying permeability. And then in the green box, he's showing neurons like that brownish color neuron where he had intermediate to good porosity, but varying permeability. And let me just move forward for time. So then on the next slide, you should be seeing cross sections from a previous study of Garrett in 2016 that show cross sections of the porosity and permeability. I forget the details of the Garrett study. I think he did some sort of reservoir analysis just based more primarily on seismic and the well data. And then below those two, Carl's showing his SOM results with just a few of the neurons turned on. And what he noticed was this blue colored neuron that you see on either side seemed to tie in well with areas that had higher permeability and porosity. And then if we go down to the next slide, which, and that's going that last slide for Carl. So what he did after this is he just compared it to two different other surveys. And he found some decent correlations between what he could do in the SOM analysis and porosity and permeability. But this, to some extent, is still a work in progress, with some of the work being currently worked on. Okay, so next one I wanted to show was a study on channel architecture. And so this is work that Corellia Lamarca did. She's now currently a PhD student, but this was part of her master's student last spring. What spurred this study is she wanted to do kind of an analysis on what would happen if you compared user versus machine selected attributes. And so I'm just going to show you the machine selected attributes because we ran a PCA analysis on that in Paradise. For the data set that we chose, it's in the Taranaki Basin, which is just offshore New Zealand, kind of on the west side of the North Island. You can see that on the upper left-hand side of the map. We chose this data because New Zealand has lots of beautiful public data sets on, with really good quality 3D seismic surveys. And so it's a deep water setting. And if you go to the next slide, this is just what the data looks like. So in the vertical section, we're showing the seismic amplitude. And then I think it's variance being shown on the time slice. And so you can see some of those channel features in the variance. So this data was acquired in 2013, 0 phase, SEG negative polarity. She had one well in there, the Potato one. The well logs went through her zone of interest, but just the gamma ray. And so she did a well tie and she used that well data as much as she could in the Miocene section. Next slide, please. Okay, and then hit one more time. Oh, I forgot I have all these animations in here. So this is the area of interest. So she selected a sub-survey of it, and that was just the area where she ran the SOM analysis with Paradise. So this is just a little bit of information on the geologic setting. This is a rift basin. It was a rift basin in the Cretaceous, and then it filled up with some nice, beautiful sedimentary successions. And the area we're looking in is the Miocene, particularly the Moki and Manganese formations. Next slide. Okay, so here we get into a simplified workflow just for part of her thesis work, where she did the well tide, looked for features of interest, figured out some of the lithologies, picked horizons, you know, all the basic early work that you want to do before you start doing an attribute analysis. And then she computed the attributes, divided them into different categories: textural, geometric, instantaneous, and spectral. Attributes, ran a PCA analysis with the Paradise software, looked at the eigenvectors to figure out what were the principal contributors, and then ran a SOM analysis. After that, she did some testing and validation and the analysis and interpretation. And if you could go to the next slide. So here is what some of the data looks like and the features of interest in seismic data. So we've got a vertical section on top and a time slice below. And what you can notice is that she put little boxes and interpretations around certain seismic facies, which were of interest to her that she noticed in the seismic amplitude. So once recognizing some of these features, you know, traditionally this would help steer us in picking out which attributes to use, but we wanted to let PCA do that on our own and see what it came up with. So if you could hit the next slide. So here are the PCA results. So she ended up putting in 28 seismic attributes, and they're all listed there. She let PCA do its thing, narrow down the dimensionality of the data, and she ended up picking out 9 seismic attributes that had the highest levels of independence. And so with that, they represent most of the variability in the data. And so you can see they're listed down there: the cosine of instantaneous phase, the original amplitude envelope, some GLCM attributes, and then a couple curvature and the sweetness. Next, please. And you could click through these. So here she first looked at her area of interest, neuron by neuron, like a nice thorough analysis, trying to see which neurons, which multidimensional attribute combinations were giving her some interesting results and what we would think are geologic features. And so just to point out quickly at the, I can't quite read these, but you can see that some of them have more geologic shapes, and then other neurons are essentially empty or kind of just picking up some of the edge noise. And so these were ones that she could quickly identify as not being important in helping the interpreter understand the channel architecture. And so next we're showing a box where you can kind of see the vertical section and a time slice of some of the more interesting attributes, neurons that we selected. And then if you could click a couple more times to bring everything up. And so zooming in, you can see she ended up selecting 6 neurons. And then with her amazing stratigraphy, she is a student of Dr. Slatt, so she's great at understanding sedimentology and stratigraphy. She went through in detail the neurons to understand the channel architecture. And so you can see here she thought that neuron 1 was most likely related to silty muddy bars. The yellow ones seem to more likely represent sheet sands, the brown ones sandy bars, pink overbank splays or levees, and then the blue ones seem to have the characteristics of more chaotic flows and mass transport deposits. So we thought this was really interesting to be able to tie single neurons to different elements of the channel architectures in the deep water system. Next, please. Yeah, and then, here we're just kind of showing how that fits in more of a schematic with the layered channel fills that you can see in kind of the green and yellow on that last slide. All right, so here's just a few more results, just showing the difference of what SOM analysis can reveal compared to our standard amplitude data. I always find it great to compare our machine learning results compared to the seismic amplitude data, just so you can see how much additional information these methods can provide. And so we've got some time slices and vertical slices showing the difference. And then as well as some different colored arrows that point out some of her interpretations. And if you'll hit this one more to bring up these. So here's kind of the analogs or schematics of what we would expect in this type of deep water system. And so you can start to see what might be some scroll bars, different parts of the channel complex, the MTDs, and the more chaotic by the red arrow. Next slide, please. Oh, yeah. So there's Corellia. Their magnifying glass. So just to conclude, if you could hit it about 5 times, it'll bring up 5 different sentences. And then one more, I think. Okay. So these are some of the main conclusions of Corellia's study. I want to highlight the 3rd and 4th bullet point because they're more related to the SOM and PCA analysis. And so what we found is that PCA did a great job in reducing the dimensionality of the attributes that we were using to let us use a smaller data set that in itself contained most of the variability in the data. And it was also the quickest way to explore a data set. So it was much more time efficient than the second part of her master's thesis, where she went through and did a user selected attribute study to compare the results of SOM between when the PCA did it and when Corellia did it as an expert sedimentologist. So PCA is great for doing your quick first look at the data set. So the machine learning helps us save time, but it's still really important to have the interpreters to validate the data. So we are still important as geologists and geophysicists, and we don't think the machines will replace us yet. All right, so if you go on to the next slide, I will quickly cover the last case study that I wanted to show. So this is the second portion of Julian Chenin's master's thesis, where he's looking at undersaturated gas. Next slide, please. And he's typing this up now so that he can defend next month. All right, so just to kind of quickly summarize, some of you guys may have heard of the term fizz gas. That's kind of a nickname, but what we're referring to is gas saturated reservoirs that are undersaturated or have a low saturation of gas, so they're not economically viable in the hydrocarbon scheme of things. Of course, there's motivation for de-risking and avoiding drilling an economic process. And so he used Paradise software, PCA, and SOM analysis to try and see if he could differentiate in areas where we have a saturated reservoir and an undersaturated reservoir. And so the first example I'll show, again, where he kind of refined his methodology and then tried to apply it to different areas. He did most of his work on this King Kong Lisa Ann prospect, or drilled prospects that are in the Gulf of Mexico in the Green Canyon area, if I'm remembering correctly. And so in that upper vertical slice on the left-hand side, you can see the bright amplitudes that are related to the King Kong prospect. This one was fully saturated, a successful economic well. And then if you just move up dip a little bit, we have the Lisa Ann prospect, which amplitude-wise looks very similar. It's a default to always a little riskier, but it still retains those brighter amplitudes. And so in this area, the company drilled the well and they found that it was unsaturated and uneconomic. So the seismic data, we're looking at it and it's telling us, hey, these two things look similar seismically, but they're actually not in terms of their gas saturation. And so that was the puzzle I sought him out to solve, to see if SOM analysis could help us differentiate between these two reservoirs. And then we also applied this kind of shown below in the URSA, so the lower vertical section, the URSA reservoir, which is also in the Gulf of Mexico. And then just last month, he looked at applying these methods to the Scarborough field in the Carnarvon Basin on the northwest shelf of Australia, so moving across the world. Next slide, please. Okay, so the crux.
Hang on, sorry, I think I skipped one.
Yeah, you did. It's kind of the important theory one. So
hold on a second.
That's okay. I think you went the wrong way.
Let's see that.
So 42. Go to 42.
42. There you go. Sorry about that.
That's okay. So just to spend 5 seconds talking about the theory, with increasing gas saturation, the bulk modulus doesn't change too much. So you can see in the green line on the right-hand side that partially saturated gas reservoirs have similar bulk modulus to fully saturated reservoirs. So there's just a very, theoretically, there's a small difference between them. And so this ends up affecting the seismic velocity and therefore the acoustic impedance and the reflection of the seismic data. And so machine learning, we're hoping, is able to differentiate these very small changes. All right, next slide. Okay, I don't know if you guys are looking at it, but I'm going to talk. So here's the geologic background, here we go, of the King Kong Lisa Ann area. So I'm showing that cross-section through the seismic that we already did. So this is deep water. The King Kong was a structural four-way closure. The Lisa Ann was on the hanging wall of a large normal fault. And this probably ended up being the seal failure that allowed it to be undersaturated. So both of them have similar seismic amplitude anomalies that you could see, but Lisa Ann ended up being uncommercial. Next slide. So, and then you could hit it one more time to show the results. So here's the amplitude section. And then what Julian did is he ran a PCA analysis and a SOM result. This one's showing all of the neurons in the 5x5 that he got. And then if you can go to the next slide. All right, there's where the wells are. Hit it one more time. Okay, and so here he highlighted just two neurons, neuron 3 and neuron 4. And so what we noticed here is that these two neurons seem to show that there is something slightly different between the King Kong prospect and then also the saturated, undersaturated Lisa Ann prospect. Now if you'll go to the next slide. So what he ended up doing, and hit it one more time, is he took the same parameters and the same, I keep hitting it a couple of times. And then once more. Thank you. Okay, so he ended up taking the same attributes and trying to repeat these results in the URSA field, which is nearby in the Gulf of Mexico. And what's interesting about the URSA field is there's some well log data available there in a study that Fred Hilterman did a while back. He was able to point out, as you can see on the right, that certain reservoirs were more fizz prone, so undersaturated, while other ones were full of oil. And so you can kind of see these different, I'm using my mouse to point this out, but you can see the different higher amplitudes related to these different hydrocarbon reservoirs. And so what's cool about this study is that now instead of comparing two fields that are separated by a few miles, now we can look at reservoirs within the same wellbore. And so using the same attributes as before with the King Kong Lisa Ann, we get the SOM result that's shown on the left. And then if you can go to the next slide, what he did is he highlighted perfect. Just two of those neurons that seem to highlight the more oil-prone reservoirs that end up being more pronounced in the SOM analysis. I should mention here, because I see the words probability threshold, is that Julian really used the probability threshold capabilities of the Paradise software for both this undersaturated gas project and his hydrates, because the probability of either of those happening is kind of on the lower side. So he looked for what was less probable, if I'm saying that correctly. And so what I'm just trying to show here is that we have some different results depending on if they were fizz related or oil related. So they were still pretty optimistic about this. So going on to the next slide, last month or so, Julian started trying to apply this to a Scarborough field offshore Australia to see if he could use the same attributes and get similar results. And so what's interesting about this is we're working in a totally different geologic setting. Some work with the Scarborough field believes it's undersaturated. We're talking to somebody at AAPG, Julian was, where he showed this work, and they were suggesting that there was probably some sort of seal failure here that led to the undersaturated gas in this area. And so if you could go to the next slide. Okay, and then hit it one more time. So here's the amplitude section, kind of outlined in black is the 50% saturation outline from a previous study, Ray et al. In 2014. So that kind of shows roughly where we've got more of the undersaturated gases. And so showing the full SOM result, I think if you click it one more time, it will show us just selected neurons. Julian selected just 3 neurons that seem to really highlight where in that amplitude anomaly you have some of the undersaturated gas. And so the results here, with playing around with the different neurons and changing some of the parameters, Julian noticed that we don't see a great discrimination between the low and high saturated gas zones. And so that kind of is telling us that there's something different going on in the rocks in this area in offshore Australia versus what we were able to replicate in the Gulf of Mexico. If you could go on to the next slide. So the next slide shows the different neurons that Julian had selected as being important to identifying the undersaturated gas reservoirs, as well as the attributes and their neuron and total independence. And if you click a few times, what you'll notice is that the envelope tended to be one of the most important neurons, and then sweetness the second. And so we're still trying to figure out some of these results and exactly what they're telling us between the Gulf of Mexico wells and fields and the Scarborough fields. But we're seeing some consistencies between the two. But right now, I don't think we have super definitive ideas on what's going on. But some analysis does seem to be showing us in some cases that we can qualitatively tell the difference between undersaturated and saturated gas reservoirs. So if you go one more slide, I think this was one of my almost last slides. Yeah, and click it a few times to bring up all the pictures. So where we're at with this SOM analysis and undersaturated fizz gas conclusions is that we're seeing more qualitative differentiation, but it seems to just be working primarily for the GOMS data set. So we don't have confidence that this method is transferable to other parts of the world with different rocks and tectonics and properties. So it didn't work well using the same technique in the Scarborough field. And then if you could hit it 1 or 2 more times. Cool. Yeah, and so this is just kind of like some summary figures of what we were able to see, and then hit it a couple more times. Got a lot of animations on this one. So just kind of highlighting the King Kong and the Lisa Ann, and then if you hit it one more time, I think it should show Scarborough on the results. Nice. So that's where we wrap up on this case study. And then if you could click the slide one more time. You know, we of course want to acknowledge Geophysical Insights for providing the University of Oklahoma with Paradise software that has allowed us to do these studies as well as a few others. You know, we're with the School of Geosciences. Schlumberger provided us some software, the Petrel software. We're part of AASPI. I'm part of AASPI, so we're using AASPI software. Consumers Energy gave us the waste data, and then New Zealand Petroleum Minerals and GNS, and then also the USGS provided us with some other free public data sets. So with that, I can take questions. Thank you for putting up with some of those technical difficulties. Sorry, I couldn't use my mouse to point out all the interesting features.
I think your arrows did a really good job.
Yeah. Well, I have to credit, you know, my students made about 95% of those slides, and I just mashed them all together. So they're great presenters.
It worked. It worked. So just to remind you guys, you can type your questions in the chat, or if you're watching via YouTube, and in the comments section. And we'll hang on here for a couple of minutes with Heather, so to give you an opportunity to do that.
Yeah, and then since I see Julian and Corellia hanging out, they could probably answer a little bit more detailed questions than I can, because I just review their work from a higher level, as they are great scientists on their own.
It's a good thing it gives me like the little 3 dots so that I know people are like furiously typing.
They're typing.
Yes.
Okay. I can't see that. So I'm like, okay.
Gonna give them an opportunity.
Please everything or everybody fell asleep.
You students can go and see your wonderful accolades in the chat.
Yes, everybody is saying you guys did a nice job. So I will mention, let's see, Julian's hydrate work has been accepted, and we're finishing the revisions. So when it's published, we'll put it up on the AASPI website, so you can see more details. Corellia, some of her work has been accepted. Another part of it we just submitted to be part of a book chapter today, I think. But everything that we do when it's published, and even some of our SEG and ACE presentations, we're putting up on the AASPI website. And those will have a lot more, you know, details about the workflow and our thinking and interpretation.
Okay.
And you guys can, of course, always send me an email if you have questions that keep you up at night regarding this presentation later.
There you go. All right, well, I think with that, we're going to go ahead and close it out and get ready for the next presentation. Our next presentation is by yours truly, and it's going to be a little bit of a deviation from all the wonderful geoscience presentations that have gone on so far. And we're going to talk about building your personal brand as a young professional and how that looks, and becoming a thought leader in your field. So it's tangentially related to the fine topics and the fine work here that the students have done. So very good. Any other closing comments, Heather?
No, just thank you everybody for paying attention. And you know, this was a nice software that we've been having a lot of fun playing around with at the University of Oklahoma.
Wonderful, wonderful. All right.
Science is fun. Science is fun.
Well, thank you very much, everyone, for joining us. And the recording will be available later if you check back tomorrow. And we'll see you here shortly at 4 o'clock. Thank you very much. Have a nice afternoon.
Thank you, Laura.
Bye-bye. I'm so glad you told me. All right. So I'm just going to say that again. So I was just saying, you may have noticed that I've been introducing all the presenters for Geophysical Insights all day today. And the process here is going to be much the same, only now I get to introduce myself. But as always, you're welcome to put your questions in the chat box, and I'll get to them at the end of the session. If you're watching via the YouTube live stream, you can put them in the comments, and we'll get to those as well. A little bit about me. My name is Laura Cuttle, and I'm a marketing manager with Geophysical Insights. I'm actually practice lead for a company called Advertos. We're a marketing and public relations agency located in Houston. And we've been working with Geophysical Insights for probably the better part of 10 years now, maybe a little past that at this point. But it's been our great pleasure every year to help them with their SEG booth and the other shows that we do, and all of their wonderful initiatives in terms of Paradise. So Tom, the CEO, asked me if I would present on something this year. And, you know, in thinking about it, we have a lot of students and young professionals that come by the booth to learn more and augment their knowledge. And that's great. And we support the students as we do. You know, Heather Bettel just spoke, and a lot of her students were on, and, you know, they're very near and dear to our heart. So today I'm going to talk about something a little bit tangential to geoscience. We'll take a break from the highly technical presentations that we've heard all day, and we're going to talk about managing your personal brand. So every day I am so blessed to be able to work with highly intelligent people that publish in peer-reviewed journals and do amazing, incredible work. And, you know, part of my job in marketing is to communicate that, to let everyone know, to really push those messages out. And so in thinking about something that would be useful to a wide range of people, you know, I really wanted to just take a little bit of time and comment on the ways that we do that, how we build as young professionals, how we build our personal brand. And I know I haven't even gotten to the first screen yet, but let me just tell you a little bit about what this presentation is and is not. This is not a corporate marketing presentation. It's not about marketing a corporate brand, right? When I talk about your personal brand, I mean communicating who you are to the industry at large that survives multiple jobs. And no matter where you are in your job life cycle, whether you're looking for a job, whether you're looking for a promotion, whether you're just getting started, whether you've been in a while, you know, your personal brand is how the industry views you, and you'll continue to build that across time. So moving forward. So, you know, today we're going to look at a little bit of how this happens. This is kind of a personal brand 101 presentation. If you're very active and you know a lot of the things to do, then maybe a lot of this information isn't going to be new to you, but hopefully there'll be some tidbits that you can pick up along the way. I've been doing this for 20 years, and there's some things that are fundamental basics that everyone should do, and you know, they're good suggestions for a reason. And then there's some tips and tricks I've learned over the years that I'm going to share with you guys. So really, in essence, you know, you look across the industry and you see these people who are very well known, and they're considered thought leaders, and they get asked to speak everywhere, and they get asked to be co-presenters or co-publishers on something. And so if you've ever kind of wondered yourself, how did they get to that position? How did they get to have that kind of reputation in the industry? We're going to talk about how they did that. And of course, how that happens is much, much different now than it was even 5 years ago. I mean, especially 10 or 15, but it's changing so rapidly all the time. But the fundamentals remain the same. You know, in order to build your professional brand, it really requires some focus. It starts with your message. You have to sit down and look at, who am I and what I'm about? What kind of things motivate me? What kind of opportunities excite me? What adjectives have people used to describe me? The positive ones. We'll set aside the negative ones for now. Have you had any unique experiences? You know, it lacks credibility to say I'm good at everything. Although, you know, when you're kind of starting out, you may not know what you're good at yet. But it's important to find a focus, find an area of expertise, a track that you can really like dig down deep into. And then once you kind of have that message together, we're gonna talk about each of these pieces in the presentation today. You're gonna communicate that message. You're gonna curate content online. I'm gonna tell you a little bit of ways to do that. Participating in online discussions, again, some helpful tricks on how to do that. and making meaningful connections, not just any connections, but making meaningful ones and how to do that. And again, the process continues, communicating your message to those new meaningful connections. So let's talk a little bit, obviously we live in an online world, as evidenced by our virtual presence here today. COVID has pretty much caused us all to move on, like completely online. I saw a joke the other day that said, who is in charge of your digital transformation project? Was it your CTO, your CEO, and then there was option C, COVID. While it's a little politically incorrect, I think that holds true for a lot of us. There was people who hadn't quite made fully a transition to an online world until they were forced to. So as you're looking across the platforms that you could be active on, what it's really important to know is, first of all, we're going to take a separation between your personal platforms and your business platforms. You might be an Instagram just superstar, and you might be posting pictures of the vacation that you went on and the dinner that you had last night and the fun time out that you had, and that's great. That's personal. That doesn't belong in a work environment. So what you want to look at first is, where are your colleagues? Typically, my experience has been LinkedIn, Twitter, particularly in the area of exploration and development, and in this oil and gas industry. That's where people are. And it's important to create a cross-platform plan. So one is good, more is better. Too much and you lose focus, and you probably don't have time for the others because they all require a little bit of tweaking. So I wouldn't say tackle everything, but pick like the top 2 or 3. Let's just take just a second and talk about a website. I know there's a big push, and I've heard, college counselors say, put up a website, put up a website. Well, having hired a lot of people before, I'll tell you, if you don't have any new information to put on your website that I haven't already seen in your resume, don't waste my time. So before you go to the effort of having a website and putting things on it, ask yourself some questions first. Do you have a portfolio of work that you have to display? Have you been published in a variety of sources? If you've been published in one place, you can put a link to that on your resume and be done. But if you've maybe been published in 3 or 4 places and want a better way of displaying it, or talking about those, then a website might be the way to go. Certifications. If you have some that require additional explanation, in my line of business, the things that are applicable are things like a PMP, Project Management Professional. Everyone knows what that is. There's one certifying organization. You put PMP behind your name. Very cut and dry. However, there's others, like I have some certifications in UX design. That's much more, requires some description. So some UX design courses have, specific tracks. They have different certifying agencies, all kinds of things. And so, those are maybe some things that might merit a little more discussion, or a place to expound on them a little bit that just makes a resume too long. So maybe that makes some sense. In terms of blogs, I get this question a lot. Is it worth it to have a blog? Well, the answer is that really depends. Do you have time, and do you have enough to say on a given topic to pay attention to it and put something out there at least once a week? If you don't, I wouldn't really bother with it. Blog content that's like once a month or once when I feel like it just really doesn't gain any traction, and it's kind of wasted effort. Whether you put it on a separate website or whether you put it within LinkedIn, totally your call. It doesn't really make a hill of beans difference. The only kind of minor difference it makes is the website crawlers have an easier time crawling a website, a public website. Sometimes, depending on your permission controls in LinkedIn, the website crawlers may not be able to see those. So it might be better to have it on a website. But again, that's kind of a detail. I would say, by and large, wherever you choose to put it, put it. So let's talk about building a great LinkedIn profile first. Again, there's a lot of places to start online, and this is just the building blocks that really make a big difference. So I'm going to switch back and forth while we're talking here between LinkedIn Live and my PowerPoint presentation. So bear with me while I do that. But here I have a sample of a really basic profile. And I am going to go pick on my dear friend Emily. And I can pick on her because I've told her this directly before. And so she and I have had this conversation, so she won't mind. But you can see she's got a picture. Okay, that's fine. She has nothing. She has no about. She just lists the places that she's worked. She's got a couple of endorsements, and that's it. You know, LinkedIn really provides you a great space to be able to put a lot of information in. So hang on. Now I can't get my PowerPoint back. Just a second. There we go. Okay, so let's talk about what kind of things makes a good one versus a bad one. And we'll go to Allie Miller's live one in just a second. But graphics. So again, this is super important. When you're considering what you're going to put for your profile picture, go invest in a professional headshot. People will use it for everything. We host conferences, we host events, we do things like organize the speakers for the SEG booth here. And the first thing when we get a new speaker in is we say, give us your headshot. So if you at all want an opportunity to speak, having a good headshot is very important because it allows the marketers of those events to take your very nice headshot and make reasonable marketing materials out of it. And that's the first thing they're going to do is they're going to say, can I use your LinkedIn profile picture? And if they go to your LinkedIn profile picture and it's a picture of your cat or a picture of you in a swimming pool or something like that, we can't use that. So having a headshot makes a great first impression and it makes you look prepared for opportunities should they come up. As far as your banner here, again, she's got a very nice one, but there's lots of free artwork you can go look at online. Pexels.com is free stock photography. Go pick something out, use it, that's great. If you decide to go onto Google and pick out a pretty Google image that you like, that's actually okay. You do have to credit your source though. So if you get it from whatever news site, right? You look at the bottom of the picture and find out who took the picture and then just put in a little watermark on the bottom, credit such and such, news site or whatever that published the picture to begin with. Moving right along, you can see Allie Miller right here, right underneath your name on LinkedIn, you've got a headline. 9 times out of 10, I see people's headline and it has their job title and the company they work for. That's fine, but it's really a missed opportunity. So this headline right here describes you. It describes what you're all about. You can see here she has put her accolades that she's gotten. If you happen to visit my profile, I put the various things that I have expertise in. But it's an opportunity to make it different from your job description or your job title such that people can find you better. People immediately at a glance know who you are and what you're about. Remember, you're not selling yourself as a particular role at a particular company because that's temporary, that can change. You're selling yourself as a whole. This is a brand you're building. And theoretically, you might hone that message a little bit, but it's not really going to change over time unless you have new experiences and want to add to it or something like that. The about. You're going to use your description to summarize your strengths. I know, and I would say this is about 50-50 on the different profiles that I visit. Some people have this, some people don't. They're a lot better about filling this out than they are making their headline unique. But you can also use this opportunity to let people know what they're going to get by following you, what kinds of content you post, what's in it for them. And we'll come back to that in a little bit. Then please give each job you've had a detailed description. So keep in mind, and I know you've been told this 100 times before, but it bears reiterating, we have to write for computers and people today. We have to write so that it's interesting for a person, but you have to include enough keywords so that you come up in a search. So if you've had particular area of expertise, say you've done Python coding, great, put it in there. If you've worked in the Permian Basin, put it in there. If you've, any kind of a thing that someone might search on, you want to make sure you get those keywords in there, provided you still want to keep doing that thing. If you aren't interested, then leave it off. So, and then the last part is consolidating your recommendations. So recommendations, I will say, the difference between 0 recommendations and 3 or 4 recommendations is huge. You should have some. The difference between 5 recommendations and 10 recommendations, not so much. So there's a point of diminishing returns, right? But it is helpful to have several really well-written recommendations. So every time you have a positive interaction with a boss, a coworker, a client, someone, see if they'll go in and write you a positive review on your LinkedIn or wherever else you decide to do that. If you have another platform that you prefer, the idea is to consolidate those all into one so that you're not asking people to go to several different places. All right, so let's talk about becoming a thought leader for a minute. We're going to kind of revisit this concept. So what kinds of things make up a thought leader? We toss that term around a lot. You see it all the time in all kinds of marketing material. I kind of think it's overused, but it captures, what we mean. They are an expert in a discipline. So they're people that are looked to for their opinion on things. They're a contributor to the body of knowledge. They're doing new work. They're producing value. They're also a trusted collaborator. They're people that work well in a team, that are looking out for the team's best interests, that keep information secure, that really step up to the plate and do their part and make the whole thing a success. They're people that when you look across the crowd, you say, I want to work with that person, because if I'm with that person, I know we're going to do something amazing. And so it's really, when you're thinking about putting yourself in that light, you really want to incorporate the kinds of attributes that encourage that kind of thought process. So how do we get the word out? Like how does this happen? Very tactically. I'm going to say publish, publish, publish. And to this crowd, that means something a little different to you as a geoscientist than it does to me as a marketer. When I say publish to you, generally people think, oh, peer-reviewed journal. That's great. You should do that. Not taking anything away from that. But there are so many other opportunities too. People who write for a living, like me, have a ravenous appetite for content, particularly people who have to push out a lot of content all the time, any reporter of any kind. So there are all kinds of industry magazines that need stories. They need legitimate stories. There's Hearts E&P. There's, the AAPG magazine. There's, all kinds offshore. I work with all these guys. I should be able to come up with a lot more. Houston Business Journal. Don't forget the local papers. Even your HR departments at your large companies, they are in a way a publisher because they're always trying to recruit new people, new talent, and they need stories. They need stories just like anything else. They're selling, in that case, a job, but in the same way that we sell products or other things, they need stories. And so you can always just reach out to the reporters. You can find them on LinkedIn. That's a great way to reach out to them. And ask, tell them about a project that you've had recently. If you've had a great success, call them up, tell them about it, pitch it, see if they have anything to say about it. There's also a website. It's called HARO, Help a Reporter Out. And basically with that, you sign up and you say, I have expertise in this field, this field, and this field. And when a reporter has a topic that matches with the fields that you have expertise in, they email you and ask for your opinions. And so that's a great way to connect with reporters who are already writing on those kinds of stories. So opportunities to speak. Industry associations, yes. There are a lot of people speaking at SEG all over today. That's wonderful. I applaud them. There may also be other opportunities. User conferences. Do you use software all the time that you really enjoy, that you've done something great with, and you want to show it off? Chances are they want to show it off too. So I've had opportunities to speak at user conferences for software that we use, our CRM software and other such like, and so that's been a great opportunity too. Networking groups, even if they're local networking groups, opportunities to speak on things that you are passionate about or you have great experience in. And then participating in conversations. Now these, a little bit different than speaking, and this is more the back and forth, right? So this is participating in the LinkedIn groups. And by participate, I don't mean join and lurk. Like lurkers don't really can provide value or just pop in and like, hey, great job or whatever, like really get into providing decent content to them. And we'll come on in a minute to what kinds of content to present, but participate in a meaningful way. Quora, Reddit, there's all kinds of places online where you can jump in and really be a part of those conversations. So we're going to talk a little bit about take a little bit of break and talk about common social media pitfalls, personal versus professional. So understand first, again, your personal is your personal and your professional is your professional. Nothing of what I'm going to say relates to your personal. Do whatever you want to in your personal. Your professional life doesn't care or shouldn't have access to it. So first things, don't post things that aren't in line with your brand. So your sister is having a pampered chef party. Don't post that. It's not, I cannot envision a world where as a geoscientist, that's in line with your brand. Don't post it. Somebody's asked you to follow their pet project that they're a part of. If it has nothing to do with your career, don't follow it. Only post things, follow things, like things that are in line with your brand. Then second, do not disparage others' ideas or opinions. When you're involved in these conversations online, remember, thought leaders are trusted collaborators, right? Trusted collaborators don't get involved in long drawn out arguments. And I see it every single day on my LinkedIn feed as I'm scrolling through. Professional people that are in my network that I know, are engaging in really just divisive conversations. And, that does not improve anybody's view of their ability to work as a trusted collaborator. What to do instead? Thoughtful, respectful discussion. My mom always used to say, if you ain't got something nice to say, don't say anything at all, right? If you have a different opinion, that's okay. Beauty of social media is it allows for an open forum of intelligent, thought-provoking discussion. That's okay. If it goes in a different direction than that, get out as quick as you can. So there we go. So one other topic on personal versus professional. Do not connect with your professional contacts on personal sites. Just don't do it. It's probably not a great idea to connect with personal people on professional sites, but that happens a lot more often. That's kind of a judgment call. Why? Well, because you're going to post about your weekend, about your kid, about any kind of a thing on your professional sites, on your personal sites. And if you're connecting with the other professionals that you network with, that's going to affect the way they see you. I would highly recommend locking down your private accounts so that when recruiters, not if, but when recruiters go check out your personal Facebook, your personal Instagram, all they see is a profile picture. That they will check, they do background checks. And I, as a hiring manager myself, often go check people's backgrounds. And if I can't see it, that's fine. I don't look anymore. They've locked it down. That's their business. If they're putting out there for the world to see, they're partying for the last 3 weekends, that's not an impression that I want to leave my clients with of our team. And so that would really affect, the way that I see them in a hiring sense. We're going to touch on 2 kind of touchy topics, but only because they need to be touched on. And we're going to do it ever so briefly. Please don't post about your political views on your professional sites. It's just not appropriate. You may have very strong views, and that's fine. Your personal social media is the place to do that, not your public one. You can promote ideas that unify people. So if you go to major people like Richard Branson, for instance, he's huge on his personal brand, right? He's got a lot of companies, but he's got Virgin Airlines and Virgin Records and so forth and so on. But Richard Branson, the brand, is separate from any of those companies. And if you look at his personal feed, he cares about a whole lot of topics that are humanitarian in nature. And that's great. Sprinkle those in. But in terms of posting on divisive political things, doesn't have a place in your professional feed. Same thing about religion. Unless you are a member of the clergy and that is your profession, it doesn't belong in your professional feed. Now, that being said, there are things that views you might have as a result of your religious views. Like you might care about feeding the homeless or, adopting foster care children or whatever like that. That's great. Do those things. You can feel free to post about those things. You can communicate your values. That's part of what makes you who you are. And that's important, and people respect that. I would say be authentic. Be specific and be authentic. If you have a personal passion for bettering the world in some way, that certainly has a place in your professional life. You can sprinkle it in, Be focused about it and be authentic, because people can smell fake a mile away. And so if you're just posting things to sound like this altruistic do-gooder, people can kind of tell. So that's all I will say about this. All right, so what should you post? So you're going to post with a WIIFT. What does that stand for? What's in it for them? An audience first mentality. So think about, before you hit post on anything, think about what value this is going to bring to someone else's life. How is this going to help them do their job better, be more educated, whatever. Like, always look at it with the value that it's providing. When you think about your frequency of posts, LinkedIn recommends that you post once a day. HubSpot says that if you post more than once a day, you're basically spamming people and they get annoyed with that. So don't do that. I think like 3 times a week is a good aim to shoot for. To find unique content once a day takes a lot of time, and most of us don't have that kind of time. So 3 times a week is about a good frequency. So what should you be posting? Here's a big passion of mine. Being a pipeline of information. Any of us in our jobs are always seeking to hone the edge, right? To get better. And so we should be reading voraciously blogs, listening to podcasts, reading books. I know that's a little bit of a lost art, reading books for fun if you're not still in school, but super important. News articles, right? You should be devoting at least 30 minutes a day to just reading. Just read something. If you have a lot of windshield time like I do, books on tape. I am a huge Audible fan because I'm always driving back and forth between Houston and Austin. I have tons of windshield time. So I listen to books on tape. I listen to podcasts. And then when you find those nuggets of information that you find very helpful or enlightening or a different way of looking at something, post that in your feed and let other people benefit from that too. When you're looking at what do I post, you don't constantly have to come up with your own unique original ideas. That's not really the way the creative process works. You know, our ideas come about as generally standing on someone else's shoulders. You know, you hear something, you read something, and it makes you think, and boom, you have a new idea of your own. So, and people also really value sources of information. So, you know, posting, hey, you know, I recommend this podcast. He said such and such the other day, and here's my commentary on it. You know, even if it's like 2 lines of commentary, that's fine. But it's just think of yourself as a pipeline of information. You're taking it in and you're passing the useful stuff on. There's a couple of online resources that I was going to comment on here. There's one called Instapaper. There's another called Listly. And what these types of services do, these are just 2 examples, but these types of services go out and search the internet and find articles that are relevant to what you want to read about, and they help you put them together in a cohesive way to repost them. It kind of does your research work for you. And so that's kind of helpful if you're a little short on time like most of us are. So there we go. Oh, so another word on posting. Always, always, always post with an image. I don't know if you've observed your own habits, but I bet you as you're scrolling through your feed, you don't stop on things that don't have images. Images catch our eye. It's the way our brains are wired. So, you know, you can go online and grab an image. Again, free stock photo sites. You can take somebody else's picture as long as you credit them, whatever, right? Good news, if you're copying over a link, usually the main link, main image from the page will pull over into your link and automatically provide you an image. So that's good. But if you're reading a book, feel free to take a picture of it. We all have phenomenal phones now that take great pictures. Set your book on the table, take a picture of it, post it with your commentary. Number 3, hashtags, world of hashtags. Please don't go overboard with your hashtags. 1 or 2 are fine. They're useful. They do help people find what you're trying, what you're talking about. I wouldn't say that that's the primary way that people find things. So, to me, and this is just a personal preference. You might prefer different. That's fine. We can agree to disagree. But don't go overboard on the hashtags. It's kind of annoying. All right. Any questions? Actually, you know what? Right before I do, I told you I was going to go through some live ones, and then I kind of sped through my presentation because flipping back and forth was difficult. So let me get Heather's presentation out here out of the way. And let me just show you some things that are kind of illustrative of some of the points that we talked about. Nope, not you. Here we go. All right, so some samples of people I know. Be careful what you like and comment on, because it all shows up in your feed. So this gentleman right here is one of my connections, and he is actually one of our speakers for the Oil and Gas Machine Learning Symposium coming up next month. And you will see that he is a very busy guy. He likes and comments on a lot of things. Don't see a lot of very original content from him. He's liking, commenting on everybody else's stuff. As opposed to, let's go to Allie Miller's profile here. That's now going to refresh. You can see as I scroll through her feed, most of her stuff is original comment. Like this is her replying to a comment, but again, she was the one that originally posted it. I would say a good balance to shoot for is 50-50. 50% the stuff that you're posting yourself that's original content, and 50% commenting on other people's stuff. Oh, and I had just gone through and found a great post by her, and now it's going to refresh and get rid of it. Maybe I can find it. So there it is. So this is a great example of, evaluating another article. So she hasn't just reposted. I know a lot of times people have a tendency to just like hit share and then go. This actually provides a lot more value, is her opinions on this video. And it's going to make me a lot more willing to read it, just looking at her opinion on it, right? So those are great things. Oh, it's going to reload his too. Oh, no, it didn't. All right, so here's an example of Richard Branson, who has gone a little political, but it's more humanitarian. He's got this wonderful book club that he's a part of, and he's included this opinion on Nelson Mandela, and that ventures into a little bit global and political. That's fine. That's great. That's very unifying to people and a very positive message. So this is an example of how to do something that could be construed as political. And I think that's all of my things here. Yes. So with that, I will wrap up, and you guys are welcome to ask questions. Anybody? This is where I do the little song and dance routine while I watch all the little bubbles. Glad you guys liked it. It's funny when you look at nothing but people's online presences every day, and when we go to find new speakers for events, all I'm doing all day long is like looking at people's LinkedIn profiles. It's really funny the kinds of things that you encounter and the different ways people do things. And there's something that you think, oh, this makes so much sense to me, but then many people don't do it. So what can make you truly unique or more employable on LinkedIn? I have two answers. I have one that's kind of the gutsy answer, and I have one that's probably a little more reliable. People tend to play down their strengths. When we look at the things that are unique to us, they seem normal because we're good at them. And so we take them a lot for granted. I happen to be a very organized person, but I think that everybody's organized. And sometimes I say, oh, that person just, isn't organized and they annoy me, but I don't see what I have as special until I get around, a lot of people have told me over my time that, oh my gosh, no, I really do that very, very well. So, I would say when you're looking at your strengths, look at what people tell you about yourself. And try not to see it through your own eyes. Try to, understand how other people see you, and ask them. Ask your boss, what do you think my strengths are? Ask your coworkers, what do you think my strengths are? And when you begin to see some threads there, really lay into those, promote them. Don't be afraid to say, I'm good at this. Things that make you unique are confidence in your skills. But confidence that can be supported by specific examples. There are a lot of people that have completely unmerited confidence in your skills. Don't be in their own skills. Don't be one of those people. If you can substantiate it, then do it. I think there's nothing wrong with saying I'm an expert. Don't shy away from that. And I would say that so that's maybe a gutsy way of doing that. Some people don't necessarily have the confidence or aren't experienced enough to be able to do that in a way that doesn't come across as braggadocious. The other way you can do is put specific things down. So one trick that I learned a while ago that I do all the time is, as we finish things that mean something or that we have successes in an area, we tend to forget them. And so something kind of handy that you can do is create a note card drawer. And every time you finish a project, or even if it's a little project, even if it's a 4-hour project, or maybe it's a 2-week project or whatever, write it down on the note card. Write down the specifics of what you did, just so that you'll remember the people that you worked with, what happened, and throw it in a drawer. And then when you need to put a resume together, when you need to, dust up your interview skills, you can go back through your note cards and remind yourself. And that allows you to become a better storyteller in that interview, and to put those kinds of details on your LinkedIn profile, on your resume. So, okay, at the beginning of your presentation, you mentioned about engaging in online events. How can you do that in a better way? So here's the great part about COVID. That was, an unintended side effect. And of course, COVID's a terrible thing, but it's made us go to this online world, and it has made online events so much more accessible to so many other people, right? So for example, we throw the Machine Learning Oil and Gas Symposium every year in, this year it's November 12th, but this has opened up access to speakers all over the globe, whereas usually we just have to use speakers in Houston. So what I would do is, first of all, there's lots of event aggregator sites. Oilit.com is one of those, where they will list like every event that's coming up for the next year. RigZone does a lot. They don't have everything, but they have a lot of them. Check out all the major industry associations, find their little workshops, find, these niche places, and go through the events. And there's going to be an event organizer. I promise you, for every event, there is an event organizer. Find the event organizer, send them an email, send them a LinkedIn, note, whatever you got to do to get a hold of them. And just ask them. Tell them, I have expertise in this field and this field. Are you open to new speakers? And I bet you a lot of times they'll say yes. Oh, and there's one other tip I was going to share with you. If you find someone and you need their email address, there's a lot of ways of getting their email address that you can find. There's services like Rocket Reach. You can Google Rocket Reach, and it'll help you find like onesies and twosies. Email addresses if you need to. So you have to know their name, obviously, and where they work and who you're looking for, but they can usually find an email address to maybe like a 70% accuracy. It's not 100% all the time, but if you really are like trying to get a hold of an event organizer, usually those people have their email addresses like published and out there a lot more than, say, random average person. So, any other questions? All right, well, we will go ahead and call it a day. It is 4:45. Time to go join whatever virtual happy hour you might be at this time. Thank you all so much for joining us, and I hope that you will join us back for Geophysical Insights presentations again tomorrow morning. Have a great SEG, everybody.